Space is full of mysteries, but some are so bizarre that they challenge our understanding of the very fabric of the universe. One such enigma hides within the stars themselves, an issue so puzzling that it has left astrophysicists scratching their heads for decades. It's called the Metallicity Problem, and it raises a fundamental question: why do some stars contain elements they shouldn't? The answer to this question has implications for the birth of stars, the evolution of galaxies, and even the possibility of extraterrestrial life. To understand this mystery, we must delve deep into the cosmos, exploring the life cycles of stars, the origins of elements, and the strange anomalies that defy our expectations. At the heart of this mystery lies the concept of metallicity. In astrophysics, metals are defined as any elements heavier than hydrogen and helium. That means oxygen, carbon, iron, and even gold are all classified as metals in this context. When a star forms, its chemical composition reflects the materials present in the gas cloud from which it was born. The earliest stars in the universe, called population 3 stars, were almost entirely made of hydrogen and helium, the primordial elements formed during the Big Bang. These stars lived fast and died explosively, forging heavier elements in their cores and dispersing them into space through supernova explosions. Later generations of stars, called population 2 and population 1 stars, incorporated these metals into their makeup. The expectation is straightforward: older stars should be metal poor, while younger stars should have progressively higher metallicity because they formed from material enriched by previous generations. Yet, reality is far more complicated. Astronomers have discovered stars that defy this simple pattern. Some young stars appear unexpectedly metal poor, while some ancient stars contain an astonishing abundance of metals. These anomalies challenge our models of stellar formation and raise profound questions about the history of the universe. One of the most perplexing aspects of the metallicity problem is the existence of extremely metal-poor stars in regions where they shouldn't be. These stars, some of the oldest in the Milky Way, have compositions that suggest they formed in an era before heavy elements should have been abundant. Their presence implies that they either formed from unpolluted primordial gas billions of years after the first stars had already begun enriching the cosmos, or that our understanding of metal enrichment is incomplete. Some of these stars contain traces of unexpected elements, hinting at unknown stellar processes or even exotic physics at play. Conversely, astronomers have found stars with unusually high metallicity in places where metal-rich materials should be scarce. Some stars in the outer regions of the Milky Way and nearby dwarf galaxies contain elements like iron, nickel, and even heavier elements that should only be present in stars that formed in more chemically evolved environments. This raises the question: how did these stars acquire their heavy elements? Were they somehow contaminated by intergalactic interactions? Did they form in ways we haven't yet imagined? Another dimension of the metallicity problem is the unusual chemical compositions observed in some stars. Certain stars contain anomalies in their elemental ratios, higher than expected amounts of lithium, barium, or europium, for example. These elements are typically produced in specific astrophysical processes, such as neutron star mergers or the slow neutron capture process in aging stars. The presence of these elements in young or metal-poor stars suggests that they were exposed to an unexpected source of enrichment. Could there be unknown astrophysical events that seeded these stars with exotic elements? Or are there hidden stellar processes at work that we have yet to discover? Adding to the mystery is the role of stellar migration. Stars do not remain in the same place where they formed. Over billions of years, gravitational interactions can cause them to drift across the galaxy, making it difficult to trace their origins. A metal-poor star found in the Milky Way's disk might have originated in a completely different part of the galaxy, or even in another galaxy entirely. The presence of such stars raises questions about past galactic mergers and the history of interstellar material exchange. If some stars formed from gas that was enriched in unexpected ways, could this mean that our models of galactic chemical evolution need revision? Another challenge posed by the metallicity problem is the existence of carbon-enhanced metal-poor (CMP) stars. These stars contain surprisingly high levels of carbon despite being otherwise metal-poor. Some of these stars are thought to have formed from gas enriched by the first generation of stars, while others may have acquired their carbon through binary interactions with dying companion stars. The variety of CMP stars suggests that multiple pathways could lead to their peculiar compositions, making them valuable clues in unraveling the metallicity problem. The implications of the metallicity problem extend beyond stellar evolution. The metallicity of a star has a direct impact on the formation of planets. Stars with higher metallicity are more likely to host planetary systems, particularly rocky planets like Earth. If some stars have unexpected metallicity levels, this could mean that planetary formation might occur in places we never anticipated. Could there be Earth-like planets orbiting stars we once thought incapable of supporting planetary systems? The answer to this question has profound implications for the search for extraterrestrial life. Furthermore, the metallicity problem ties into broader cosmological mysteries. If our understanding of stellar metallicity is incomplete, it could impact our models of galaxy formation and evolution. The abundance of metals in the universe is crucial for determining the age of cosmic structures, the efficiency of star formation, and even the distribution of dark matter. If some stars contain elements they shouldn't, this could indicate that unknown processes are at play, potentially reshaping our view of cosmic history. There are several hypotheses that attempt to explain the metallicity problem, but none provide a complete solution. One possibility is that some stars formed in isolated pockets of gas that remained pristine long after the first generation of stars exploded. Another theory suggests that unknown types of supernovae or exotic nuclear reactions could have altered the chemical compositions of certain stars. Some astronomers propose that galactic mergers and interstellar mixing played a greater role than previously thought, reshuffling metals in unexpected ways. Despite these challenges, advances in observational astronomy are helping us probe deeper into the mystery. High-resolution spectroscopy allows astronomers to analyze the detailed chemical fingerprints of stars, revealing subtle clues about their histories. Space telescopes like the James Webb Space Telescope are providing unprecedented insights into the earliest galaxies, helping us understand the chemical evolution of the universe. As new data pours in, we may finally uncover the mechanisms responsible for the strange metallicity patterns observed in stars. The metallicity problem is a reminder that the universe is far more complex than we often assume. It challenges our assumptions about how elements are distributed, how stars evolve, and how galaxies grow. Solving this mystery will not only deepen our understanding of stellar physics, but could also reveal new insights about the origins of planets, the structure of the cosmos, and perhaps even the fundamental laws of nature itself. Until then, we are left to wonder, what secrets do the stars still hold, waiting to be discovered? The mystery of metallicity continues to challenge astronomers as new discoveries reveal even stranger cases of stars that defy explanation. One particularly intriguing class of stars that adds complexity to this problem is the ultra-metal stars, some of which have metallicities lower than expected for their age and location in the galaxy. These stars, believed to have formed in the early universe, should contain only trace amounts of elements heavier than helium. However, observations suggest that some of them harbor unexpected elements, such as traces of iron, carbon, and even heavier elements that should not have existed when these stars formed. This discrepancy raises profound questions about how the first generations of stars spread their metals throughout the cosmos. One hypothesis suggests that these ancient stars formed in regions of space where the first supernovae explosions were inefficient at spreading metals evenly. Instead of enriching their surroundings uniformly, these explosions may have created localized pockets of material with varying levels of heavy elements. Some regions could have remained relatively pristine, while others became heavily enriched, leading to the strange metallicity differences seen in ancient stars. This idea is supported by simulations that show how early galaxies may have experienced uneven enrichment due to the chaotic nature of the first stellar explosions. Another possible explanation is that these ultra-metal stars were born in dwarf galaxies that later merged with the Milky Way. The smaller galaxies may have retained their metal status for longer periods due to slower star formation rates and weaker supernova feedback. When these galaxies merged with the Milky Way, their stars were absorbed into our galaxy's halo, appearing as metal outliers. This theory aligns with observations showing that many low metallicity stars are found in the galactic halo, where remnants of ancient mergers are expected to linger. While some stars appear to have far too few metals, others surprise astronomers with an overabundance of heavy elements. Some metal-rich stars in unexpected locations hint at processes we do not yet fully understand. For example, certain stars in the galactic halo, normally expected to be metal-poor, have metallicities rivaling those of much younger stars in the galactic disk. This suggests that they may have formed in environments where metal enrichment occurred much more rapidly than anticipated. Could these stars be the result of unusual supernova mechanisms, or did they form in dense star clusters where metals accumulated faster than in typical regions of space? One particularly striking example of unexpected metallicity is the presence of stars enriched with elements produced in neutron-star mergers. These violent cosmic events, where two neutron stars collide, are now known to be a major source of heavy elements such as gold, platinum, and europium. Some stars, classified as R-process-enhanced stars, exhibit abnormally high levels of these elements, suggesting that they formed in regions influenced by one or more nearby neutron star mergers. However, neutron star mergers are thought to be relatively rare events, which makes it puzzling that so many stars show signs of enrichment by this process. Could the frequency of these mergers be higher than expected, or is there another unknown mechanism capable of producing these elements in early stars? Adding yet another layer to the metallicity problem is the peculiar case of lithium in ancient stars. Lithium is a particularly interesting element because its abundance in the universe is predicted with high precision by Big Bang nucleosynthesis models. Yet, observations reveal a so-called lithium problem. Many metal-poor stars have significantly lower lithium levels than expected. The cause of this discrepancy remains unknown, but some theories suggest that lithium may have been destroyed in the interiors of these stars through unknown nuclear reactions, or that our understanding of lithium production in the early universe is incomplete. One of the biggest challenges in solving the metallicity problem is that stellar metallicity is not a static property. Stars can experience chemical evolution over their lifetimes, altering their compositions. Binary star interactions, for example, can lead to the transfer of material between companion stars, changing their observed metallicity. This is particularly relevant for carbon-enhanced metal-poor stars, many of which are believed to have once had a companion star that enriched them with carbon and other elements through stellar winds or mass transfer. If many stars undergo such interactions, it could explain why some stars appear more metal-rich or metal-poor than expected for their age and location. Galactic dynamics further complicate the picture. Over billions of years, stars migrate through the galaxy due to gravitational interactions with spiral arms, giant molecular clouds, and even dark matter. A star that appears metal-poor in a region where high metallicity is expected may not have formed there at all. It could have traveled from a completely different environment. This stellar migration means that we cannot always assume that a star's metallicity reflects the history of its current location, adding another layer of uncertainty to our understanding of the distribution of metals in the universe. Despite the challenges, astronomers are making progress in unraveling the metallicity problem. Advanced spectroscopic surveys, such as those conducted by the Gaia mission and the Sloan Digital Sky Survey, are providing detailed chemical analyses of millions of stars. These observations allow researchers to map the chemical evolution of the galaxy with unprecedented precision, identifying patterns that may reveal the origins of metal anomalies. The future of this research is particularly exciting with upcoming telescopes like the Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope. These observatories will enable astronomers to study the metallicity of stars in distant galaxies, shedding light on how metal enrichment progressed across cosmic time. By comparing the chemical compositions of stars in different galaxies, scientists may finally uncover the missing pieces needed to resolve the metallicity problem. Understanding why some stars have strange metallicities is more than just an academic curiosity. It has profound implications for fields ranging from planetary science to cosmology. Since planetary formation is closely tied to stellar metallicity, solving this mystery could refine our estimates of where habitable planets are most likely to form. It could also help us understand the overall evolution of the universe, providing clues about the earliest generations of stars and the mechanisms responsible for distributing heavy elements across space. The metallicity problem is a testament to the complexity of the universe. It reminds us that even something as seemingly well understood as the composition of stars can still hold deep and unresolved mysteries. With each new discovery, we come closer to unlocking the secrets hidden in the chemical signatures of the cosmos. And yet, every answer leads to more questions, proving that the journey to understanding the universe is far from over. The stars continue to whisper their secrets, and as our technology advances, we may finally learn to listen. The metallicity problem is not just an abstract astrophysical puzzle, it is a key to understanding the grand story of the universe itself. By deciphering the distribution of metals in stars, we can piece together the history of cosmic evolution, from the fiery birth of the first stars to the intricate web of galaxies that populate the cosmos today. But as we probe deeper into this mystery, the more we realize that our current models may only be scratching the surface. One of the most perplexing aspects of stellar metallicity is the existence of stars with extreme chemical compositions, those that contain unexpected ratios of heavy elements. Some stars, for example, are found to be incredibly rich in elements associated with the slow neutron capture process, S process, while others exhibit abundances consistent with the rapid neutron capture process, R process. The difference between these processes lies in the environments in which they occur. The S process takes place over long periods within aging stars, while the R process requires cataclysmic events such as supernovae or neutron star mergers. Yet, some stars display signatures of both processes, challenging our understanding of how they acquired their elements. This leads to an even bigger question: how did some of the first stars in the universe, which should have formed in pristine hydrogen-helium environments, acquire heavy elements in the first place? The presence of R-process elements in some of the oldest stars suggests that neutron star mergers or other high-energy cosmic events must have occurred early in the universe's history. But neutron stars are formed from the remnants of dead stars, so how could they have merged so soon after the Big Bang, when few stars had even completed their life cycles? This apparent contradiction forces astrophysicists to rethink the timeline of stellar and galactic evolution. Another surprising metallicity-related phenomenon is the detection of chemically anomalous stars in unexpected places. For instance, some stars in the Milky Way's halo, a region dominated by ancient metal-poor stars, exhibit unusually high metallicity levels, suggesting that they formed in environments rich in heavy elements. This could mean that these stars originated from other galaxies, later absorbed by the Milky Way through galactic mergers. In fact, astronomers have identified entire stellar streams, remnants of dwarf galaxies that were torn apart by gravitational forces, that contain stars with metallicity levels inconsistent with their surroundings. These discoveries not only shed light on the history of our galaxy but also demonstrate the complex interplay of stellar migration and chemical evolution over billions of years. One particularly strange class of stars, known as carbon-enhanced metal-poor (CMP) stars, presents yet another layer of mystery. These stars contain an abnormally high abundance of carbon compared to other elements, a characteristic that defies conventional stellar formation models. Some theories suggest that these stars were enriched by nearby supernovae that preferentially ejected carbon into their surroundings. Others propose that CMP stars were part of binary systems where one companion transferred carbon-rich material to the other. But even within the category of CMP stars, there are subgroups, some enriched with heavy neutron capture elements, others lacking them entirely, hinting at multiple unexplained formation pathways. Beyond individual stars, the metallicity problem extends to entire star clusters and even galaxies. Globular clusters, for example, are dense collections of stars that are expected to have formed in a single event, meaning all stars within them should have roughly the same metallicity. However, observations reveal significant variations in metallicity among stars in some globular clusters, implying that these clusters may have undergone multiple bursts of star formation, or that they once contained additional stars that have since been lost. Similar inconsistencies arise when studying dwarf galaxies, some of which contain stars with metallicities far higher than expected for their size and age. These anomalies force astronomers to reconsider how metals are distributed within galaxies, and whether our models of galactic chemical evolution require revision. As technology improves, new observational techniques are providing fresh insights into these mysteries. The James Webb Space Telescope, JWST, is now capable of analyzing the atmospheres of some of the oldest known stars, potentially offering direct evidence of how early chemical enrichment occurred. Meanwhile, large-scale surveys like the European Space Agency's Gaia mission continue to map the motions and compositions of billions of stars, uncovering hidden patterns that may eventually lead to a breakthrough in understanding stellar metallicity. Yet, despite these advancements, many fundamental questions remain unanswered. Why do some stars exhibit metallicity levels completely inconsistent with their surroundings? What processes governed the early universe's metal distribution, and how did they shape the galaxies we see today? Could there be unknown stellar phenomena or cosmic events that contributed to the formation of heavy elements in ways we have yet to comprehend? The metallicity problem is not just a minor astrophysical puzzle, it is a gateway to unraveling the history of the cosmos itself. Every star carries within it the signature of the universe's past, a chemical fingerprint that tells the story of how the elements of life were forged in the hearts of dying suns. And as we continue to explore the depths of space, we may one day find that the strangest stars hold the answers to some of the most profound questions about our own existence. The metallicity problem forces us to rethink fundamental assumptions about cosmic evolution, particularly the way elements are produced, distributed, and incorporated into new generations of stars. One of the most baffling aspects of this puzzle is the presence of extremely metal-poor stars that defy expectations based on current models of stellar formation and galactic evolution. These stars, often referred to as population 3 candidates or ultra-metal-poor stars, exist in regions where we would expect more chemically enriched environments, yet they show compositions reminiscent of the very early universe. Their existence suggests that either our understanding of early nucleosynthesis is incomplete, or that there are still undiscovered processes that influenced metal dispersal in the early cosmos. One particularly intriguing hypothesis is that the first generation of stars, those born from nearly pure hydrogen and helium, were far more massive and short-lived than modern stars. These population 3 stars, if they existed as theorized, would have burned through their fuel in mere millions of years before exploding as hypernovae, or directly collapsing into black holes. The nature of their explosions, however, remains debated. Some models suggest that these stars enriched their surroundings with metals in a gradual and controlled manner, while others propose that many population 3 stars collapsed directly into black holes without releasing their heavy elements into space. If the latter is true, it could explain why some regions of the universe appear to have remained metal-poor for far longer than expected. Another mystery tied to the metallicity problem is the existence of stars that appear to have formed in environments with metallicities inconsistent with the general chemical composition of their host galaxies. Some stars in the Milky Way's halo, for example, have metal content that suggests they originated in completely different galaxies before being captured by the Milky Way's gravitational pull. This phenomenon is further supported by the presence of stellar streams, long trails of stars that mark the remnants of smaller galaxies that were torn apart and assimilated into the Milky Way over billions of years. The presence of anomalously high metallicity stars in dwarf galaxies is another contradiction that has puzzled astronomers. Dwarf galaxies are typically expected to have low metallicity because their shallow gravitational wells allow supernova-driven winds to blow metals into intergalactic space. Yet, some dwarf galaxies contain stars with metallicity levels approaching those of much larger galaxies. This suggests that certain dwarf galaxies might have experienced bursts of rapid star formation, possibly triggered by interactions with larger galaxies or by unknown mechanisms that efficiently retain metals despite their weak gravity. Even within individual star clusters, metallicity presents unexpected challenges. Traditional models suggest that globular clusters, dense, spherical collections of ancient stars, should be chemically homogeneous, as they are thought to have formed in single bursts from the same primordial gas cloud. However, observations of multiple globular clusters have revealed significant variations in metallicity among their stars. This suggests that either globular clusters experience multiple waves of star formation, each with different levels of metal enrichment, or that some stars in these clusters formed from gas that was chemically altered by processes we do not yet fully understand. A related enigma is the presence of chemically peculiar stars within stellar populations that should, theoretically, be uniform. Some stars within the Milky Way exhibit unexpected overabundances of certain elements, such as lithium, europium, or even heavier R-process elements. The origins of these chemical anomalies remain unclear, but they could be the result of rare astrophysical events like neutron-star mergers, exotic forms of supernovae, or even previously unknown forms of stellar evolution. The metallicity problem extends beyond individual stars and clusters. It also affects our understanding of planetary formation. Since planets form from the same disk of material that surrounds young stars, the metallicity of a star can influence the types of planets that form around it. Observations have shown that metal-rich stars are more likely to host gas giants like Jupiter, while metal-poor stars are more likely to have rocky planets, or none at all. This correlation suggests that metallicity plays a crucial role in determining the architecture of planetary systems. However, exceptions exist. Some metal-poor stars have been found to host surprisingly massive planets, challenging existing models of planet formation. As technology advances, astronomers are gaining new tools to investigate these mysteries. The James Webb Space Telescope, JWST, is revolutionizing the study of metal-poor stars by providing highly detailed spectra that reveal their chemical compositions with unprecedented accuracy. Additionally, next-generation ground-based telescopes like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will allow astronomers to study individual stars in distant galaxies, potentially uncovering new insights into the history of metal enrichment across cosmic time. At the same time, computational astrophysics is providing new ways to model metal dispersal in galaxies. Advanced simulations, incorporating supernova feedback, stellar winds, and galactic mergers, are helping researchers refine their understanding of how metals are distributed and mixed within galaxies. These simulations suggest that metal enrichment is far more chaotic and nonlinear than previously thought, with local conditions playing a crucial role in determining how metals are incorporated into new generations of stars. Despite these advancements, many fundamental questions remain. What was the true role of population 3 stars in shaping the chemical evolution of the universe? Why do some stars appear to have metallicity levels completely inconsistent with their surroundings? Could there be unknown astrophysical processes that alter metal abundances in ways we have yet to comprehend? The metallicity problem is not just a minor astrophysical curiosity. It is a fundamental challenge to our understanding of how the universe evolved from its primordial state to the complex, structured cosmos we observe today. Every star carries within it a chemical record of the past, a story written in the language of elements forged in the depths of dying stars and violent cosmic events. And as we continue to probe the mysteries of stellar metallicity, we may one day uncover new chapters in the story of the universe, chapters that could reshape our understanding of everything from the first stars to the formation of planets, and even the origins of life itself. The metallicity problem remains one of the most perplexing challenges in astrophysics, with implications that stretch far beyond the study of stars. If we could fully unravel this mystery, we might gain new insights into the earliest moments of the universe, the life cycles of galaxies, and even the potential for life beyond Earth. At its core, the issue forces us to ask fundamental questions. How do elements propagate through the cosmos? What unknown processes govern the formation and evolution of stars? And are our current models of cosmic history missing critical pieces? One particularly fascinating aspect of this puzzle is the role of metal-poor stars as time capsules of the early universe. These stars, some of which contain nearly pristine material from the Big Bang, provide invaluable clues about the first generations of stellar objects. Their compositions suggest that the earliest stars were capable of forging only limited amounts of heavy elements before they either exploded as supernovae or collapsed into black holes. But not all ancient stars fit this narrative. Some appear to have much higher metal content than expected, hinting at unknown mechanisms that could have enriched their birth environments far earlier than conventional models predict. The chemical signatures of these anomalous stars raise even deeper questions about the history of metal dispersal in the cosmos. Traditionally, it was believed that metals spread through galaxies via supernova explosions and stellar winds, gradually enriching the interstellar medium over billions of years. However, recent observations suggest that this process is not as straightforward as once thought. Some regions of space appear to have remained metal poor for much longer than expected, while others show signs of rapid metal enrichment that cannot be easily explained by known stellar life cycles. This inconsistency suggests that additional, possibly exotic mechanisms are at play in shaping the chemical evolution of galaxies. One possible explanation for these anomalies is the existence of previously unknown types of stellar explosions. While supernovae are the most well-studied form of stellar death, they may not be the only way that metals are injected into space. Some researchers have proposed that hypernovae, extremely powerful stellar explosions, could play a more significant role in metal enrichment than previously thought. Unlike regular supernovae, hypernovae release vastly greater amounts of energy, potentially dispersing metals across much larger distances. If hypernovae were more common in the early universe than currently assumed, they could account for some of the unexpected metallicity variations observed in old stars. Another possibility is that some stars may have undergone unusual forms of mixing that altered their surface compositions without significantly affecting their overall structure. In standard stellar models, elements created in a star's core gradually migrate outward through convection and other processes. However, certain rare stars exhibit chemical signatures that suggest they have undergone dramatic and unexpected mixing events, bringing deep layer materials to their surfaces far earlier than normal. If these mixing processes are more widespread than currently believed, they could complicate our understanding of stellar metallicity and challenge traditional methods of determining a star's age and origin. Beyond individual stars, the metallicity problem also presents challenges for our understanding of galaxy formation and evolution. One major puzzle is the existence of ultra-metal-poor dwarf galaxies, which contain far fewer heavy elements than would be expected given their age and star formation history. These galaxies seem to have avoided significant metal enrichment for billions of years, raising questions about how they managed to remain chemically primitive while other galaxies in similar environments became progressively richer in heavy elements. Some astronomers speculate that these galaxies may have been isolated from major sources of metal enrichment, while others suggest that they may have experienced unusually efficient processes that expelled metals into intergalactic space. Complicating the picture even further is the discovery of metal-rich stars in seemingly metal-poor environments. In some cases, these stars appear to have been polluted by external sources, such as interactions with other galaxies or the accretion of enriched gas from interstellar space. In other cases, their high metallicity levels may indicate that they originated in completely different regions of the universe before being gravitationally captured by their current host galaxies. These observations suggest that the history of metal distribution in the cosmos is far more complex than simple, uniform enrichment over time. The implications of the metallicity problem extend even to the search for extraterrestrial life. Because metals play a crucial role in the formation of planets, their distribution throughout the universe could directly impact the likelihood of habitable worlds forming in different regions of space. The correlation between stellar metallicity and the presence of gas giant planets, for example, suggests that certain types of planetary systems may be far more common around metal-rich stars than around metal-poor ones. This raises intriguing questions about whether metal-rich regions of the galaxy are more likely to host life-bearing planets, or whether life could arise in unexpected places despite a scarcity of heavy elements. As new observational tools become available, astronomers are beginning to probe these mysteries in unprecedented detail. The James Webb Space Telescope is already revealing new insights into the atmospheres of distant exoplanets, offering a glimpse into how metallicity influences planetary composition. Meanwhile, next-generation spectroscopic surveys are providing increasingly precise measurements of stellar metallicity across the Milky Way and beyond, allowing researchers to map the chemical evolution of the universe with greater accuracy than ever before. Despite these advances, many aspects of the metallicity problem remain unresolved. Do all metal-poor stars truly represent relics of the early universe, or could some have formed through entirely different processes? What role do exotic stellar phenomena, such as neutron star mergers, gamma-ray bursts, or even interactions with dark matter, play in shaping the chemical history of galaxies? Could there be undiscovered types of stellar explosions that contribute to metal enrichment in ways we have yet to understand? Perhaps the most exciting aspect of this mystery is that it challenges us to rethink what we thought we knew about the cosmos. Every new observation, every unexplained anomaly, brings us closer to a more complete picture of how the universe evolved from its primordial state to the rich, complex structure we see today. And as we continue to explore these questions, we may one day uncover answers that not only reshape our understanding of stars and galaxies but also provide new insights into the fundamental nature of matter, energy, and the very origins of the elements that make up our own existence. The Metallicity Problem does more than just challenge our understanding of stars. It forces us to reconsider the very processes that govern the evolution of the universe. If metals were not evenly distributed across space and time, what does that mean for our models of cosmic history? Could it be that some regions of the universe experienced rapid bursts of metal production, while others remained chemically primitive for billions of years? These questions extend into some of the deepest mysteries of astrophysics, touching on topics as diverse as galactic formation, dark matter interactions, and even the fate of the universe itself. One of the most perplexing aspects of the metallicity problem is the sheer variety of metallicity levels observed in stars that should, by all accounts, have similar origins. Consider the Milky Way's halo, home to some of the oldest known stars in the galaxy. These ancient stars should have formed early in the history of the universe, long before metals became abundant. Yet, within this population, there exists an enormous range of metallicity values. Some stars are almost completely devoid of heavy elements, while others show unexpectedly high metal content. This wide variation suggests that even in the early universe, metal enrichment was not a uniform process. Instead, it may have been driven by localized events, such as the explosions of the first supernovae, the merging of primordial gas clouds, or even interactions with unknown cosmic structures. The discrepancy between metal-rich and metal-poor stars has led some researchers to propose that we are missing key ingredients in our models of how metals spread through galaxies. One possibility is that metals are not distributed evenly through supernova explosions alone. Instead, they may be carried by powerful cosmic winds, expelled by the earliest galaxies, and deposited in unexpected regions. Some of these metals could even have been blown into intergalactic space, later falling back into galaxies in ways that do not align with our predictions. This would help explain why some stars appear to have formed in metal-rich environments while others, even in close proximity, lack significant amounts of heavy elements. Adding to the mystery, some stars appear to have metallicity levels that do not match their expected ages. Normally, the older a star is, the fewer metals it should contain, as it formed before many heavy elements were created. However, astronomers have discovered stars that seem to be billions of years old yet contain metal signatures more typical of much younger stars. This has led to speculation that these stars may have undergone unusual evolutionary paths, perhaps experiencing interactions with other stars, accreting metal-rich material from their surroundings, or even being rejuvenated through mergers with other stellar objects. This raises another question. Could there be processes at work that selectively enrich certain stars while leaving others untouched? Some researchers suggest that turbulent mixing in the interstellar medium may create pockets of metal-rich and metal-poor gas within the same region of a galaxy. This would mean that stars forming in different parts of the same cloud could inherit vastly different metallicities. Others propose that some stars may have formed in chemically distinct regions of the early universe and later migrated to their current locations, giving the illusion of mixed metallicity populations where none originally existed. The implications of this problem extend beyond individual stars and into the broader evolution of galaxies. Galaxies are thought to build up their metal content over time through cycles of star formation and destruction. Yet, observations show that some galaxies, especially certain dwarf galaxies and globular clusters, remain chemically primitive even after billions of years. Why have these galaxies remained so metal-poor while others have become enriched? Could it be that some galaxies lost their metals due to extreme cosmic winds or interactions with larger galaxies? Or could there be hidden processes at work that allow metals to escape detection? This enigma becomes even more profound when we consider the discovery of extremely metal-rich stars in what should be metal-poor environments. Some stars in the Milky Way's halo, for example, have metallicity levels comparable to stars in the galaxy's much younger disk. This suggests that they may not have formed where they currently reside. Instead, they may have been ejected from the galactic center or even accreted from smaller, metal-rich satellite galaxies that merged with the Milky Way long ago. If true, this would mean that the history of metal distribution in our galaxy is far more complex than a simple, gradual enrichment over time. Further complicating matters, astronomers have discovered stars with chemical compositions that defy explanation by standard stellar evolution models. Some stars, for instance, show unusually high abundances of certain elements, such as lithium or carbon, that should have been destroyed or significantly altered during their lifetimes. This suggests that unknown processes may be influencing stellar metallicity in ways we have yet to understand. Could it be that some stars have undergone episodes of unusual mixing, bringing buried metals to the surface? Or might some stars have been affected by interactions with exotic cosmic phenomena, such as neutron star mergers or even hypothetical processes related to dark matter? The question of dark matter is particularly intriguing in the context of the metallicity problem. Dark matter is thought to make up most of the mass in the universe, yet it does not interact with light or normal matter in ways that are easy to detect. Some theories suggest that dark matter could play a role in the formation and evolution of stars, potentially influencing metallicity in ways that remain unknown. If dark matter somehow affects the processes that govern metal enrichment, either by altering the distribution of gas in galaxies or by influencing the behavior of early supernovae, then our entire understanding of stellar evolution may need to be revised. As astronomers continue to probe the metallicity problem, they are developing new tools and techniques to refine their measurements. High-resolution spectroscopy allows researchers to analyze the chemical compositions of stars with unprecedented precision, revealing subtle patterns that were previously undetectable. Meanwhile, computer simulations are providing new insights into how metals may have been distributed in the early universe, offering possible explanations for the strange metallicity variations we see today. One particularly exciting avenue of research involves studying metal-poor stars as relics of the early universe. By identifying stars that contain only trace amounts of heavy elements, astronomers can effectively look back in time to understand the conditions that existed shortly after the Big Bang. Some of these stars may even contain material from the very first generation of stars, objects that have long since vanished but left their chemical fingerprints behind. If we can determine exactly how these early stars enriched their surroundings, we may finally unlock the key to the metallicity problem. At the same time, the study of metal-rich stars is providing equally valuable insights. These stars challenge our understanding of how metals were dispersed throughout the cosmos, revealing unexpected patterns that could point to unknown astrophysical processes. By carefully analyzing their compositions and comparing them to models of stellar evolution, astronomers hope to piece together a more complete picture of how elements formed, spread, and shaped the universe as we know it. The metallicity problem is not just an isolated puzzle, it is a gateway to some of the most profound questions in astrophysics. Why do some stars appear far richer in heavy elements than others? What unknown forces shape the chemical evolution of galaxies? And could solving this mystery lead to new discoveries about the fundamental nature of the universe? As astronomers continue to push the boundaries of our knowledge, one thing is certain: the answers to these questions will not only reshape our understanding of stars but also provide deeper insights into the origins of everything we see around us, including ourselves. The metallicity problem does not just affect our understanding of individual stars. It also challenges the broader theories of how galaxies evolve and interact over cosmic time. If metals are not distributed in a predictable way, then our models of galaxy formation, star formation, and even cosmic structure formation may need to be reconsidered. This problem forces astronomers to ask a fundamental question: are we missing key processes that govern the life cycle of matter in the universe? One of the most compelling pieces of evidence suggesting that metallicity variations are more complex than we previously thought comes from the observation of stellar streams. These are remnants of smaller galaxies or star clusters that were torn apart by the gravitational pull of larger galaxies, leaving behind trails of stars that still move together through space. Some of these streams contain stars with vastly different metallicities, suggesting that their parent galaxies had complex enrichment histories. This means that even within a single dwarf galaxy, different regions may have had drastically different levels of heavy elements. The discovery of hypermetal-poor stars has also deepened the mystery. Some of these stars, found in the halo of the Milky Way, contain metal abundances so low that they must have formed from material that was only slightly enriched by the very first generation of stars. These early stars, known as population 3 stars, are thought to have been massive, short-lived, and composed almost entirely of hydrogen and helium. Their supernova explosions should have seeded the cosmos with the first heavy elements, yet the stars that formed afterward show widely varying amounts of these elements. If these ancient stars did not distribute metals evenly, then our assumptions about early supernovae and the mixing of interstellar gas may be incorrect. Adding to the puzzle, some of the most metal-poor stars also contain surprising excesses of specific elements, such as carbon or strontium. These anomalies suggest that the first metal-producing supernovae may not have behaved uniformly. Some stars may have enriched their surroundings in a highly selective manner, releasing certain elements in greater abundance than others. This could mean that our models of nucleosynthesis, the process by which elements are created within stars, need to be refined to account for unexpected variations in the way early stars exploded. At the other end of the spectrum, we find stars that are unexpectedly rich in metals. Some of these stars appear to have formed in regions of space that should have been relatively metal-poor. This suggests that certain mechanisms, perhaps powerful galactic winds, interstellar mergers, or even the influence of dark matter, may have transported metals across vast cosmic distances. If metals can be redistributed in ways we do not fully understand, then our models of galactic evolution must be reconsidered. One of the most intriguing possibilities is that interactions between galaxies played a much larger role in metal distribution than we currently assume. When galaxies collide or pass close to one another, enormous amounts of gas and dust are exchanged. This process could have led to localized regions of metal enrichment, where pockets of heavy elements formed in unexpected places. If metal-rich gas was transported in ways we do not yet understand, it could explain why some stars show metallicity levels that seem inconsistent with their surroundings. The role of globular clusters in the metallicity problem is another fascinating aspect. Globular clusters are some of the oldest structures in the universe, containing stars that formed billions of years ago. Many of these clusters show an unusual spread in metallicity, with some stars appearing to be far more enriched than others. This challenges the idea that globular clusters formed from a single, uniform cloud of gas. Instead, it suggests that multiple generations of stars may have formed within these clusters, each contributing to the chemical enrichment of the next. Even more puzzling is the presence of metal-poor globular clusters in galaxies that should have undergone significant metal enrichment. If these clusters have remained chemically primitive despite billions of years of evolution, it suggests that certain environments may have been isolated from the usual processes of metal mixing. This could mean that some regions of the universe develop very differently from others, raising questions about the large-scale structure of the cosmos. Recent studies using high-powered telescopes have begun to uncover even more extreme cases of metallicity variation. Some distant galaxies appear to contain regions that are almost devoid of metals, despite being surrounded by metal-rich environments. This suggests that even at a galactic scale, metals are not always evenly distributed. Could it be that the way metals are incorporated into stars and planets is governed by unknown physical processes? If so, it could have profound implications for everything from the formation of habitable planets to the nature of cosmic evolution itself. Another significant aspect of the metallicity problem is its potential connection to dark matter. Dark matter is thought to be the dominant form of mass in the universe, yet its influence on metal distribution is poorly understood. Some theories propose that dark matter may have played a role in shaping the chemical evolution of galaxies by affecting the movement of gas and the formation of early structures. If dark matter somehow influenced the way metals were dispersed, it could explain why some stars exhibit unexpected metallicity levels. One particularly intriguing hypothesis suggests that dark matter interactions may have created localized pockets of metal enrichment or depletion. If dark matter particles interacted with normal matter in ways that concentrated or dispersed heavy elements, it could help explain some of the anomalies observed in stellar metallicity. This idea remains highly speculative, but if proven true, it would revolutionize our understanding of both dark matter and the processes that govern the chemical evolution of the cosmos. Beyond dark matter, there are other cosmic forces that may have contributed to the uneven distribution of metals. Magnetic fields, cosmic rays, and even black hole activity could all play roles in determining where metals accumulate. Supermassive black holes, in particular, are known to generate powerful jets that can influence the movement of gas on galactic scales. If these jets played a role in transporting metals, they could help explain why some stars appear far more enriched than others. Ultimately, the metallicity problem forces us to rethink many of our assumptions about the universe. It suggests that the formation and distribution of elements are far more complex than we previously believed, and it raises questions that reach to the very heart of astrophysics. Are there unknown processes that influence how metals spread through space? Could there be missing components in our understanding of stellar evolution? And what role did exotic cosmic events, such as the first supernovae, the birth of galaxies, or the interactions of dark matter, play in shaping the chemical diversity we see today? As astronomers continue to gather data and refine their models, new discoveries are likely to shed light on these mysteries. Future space telescopes, such as the James Webb Space Telescope and its successors, may provide deeper insights into the earliest stars and galaxies, helping us understand how metals first emerged and spread. Advances in computational astrophysics will allow scientists to simulate the processes of metal enrichment in greater detail, testing theories that could explain the inconsistencies we observe. The metallicity problem is not just a technical challenge for astrophysicists. It is a profound reminder that the universe is still full of surprises. It highlights the intricate and often unpredictable nature of cosmic evolution, revealing that even something as seemingly straightforward as the chemical composition of stars can lead to deep and far-reaching questions. The more we explore this mystery, the more we realize that the universe is not as simple as we once thought. Instead, it is a vast, dynamic, and ever-changing system, where every discovery leads to new and deeper mysteries. The metallicity problem also has profound implications for our understanding of planetary systems. Since planets form from the same molecular clouds as their parent stars, the metallicity of a star can influence the types of planets that emerge in its orbit. Observations have shown that metal-rich stars are more likely to host gas giants like Jupiter, while metal-poor stars tend to have smaller, rocky planets. However, this pattern is not absolute. Some stars defy expectations by hosting planets that should not have formed based on our current understanding of metal distribution. One of the biggest puzzles in exoplanet science is why some metal-poor stars still manage to form massive planets. The core accretion model, which is the leading theory for planet formation, suggests that planets form from the gradual accumulation of solid material in a protoplanetary disk. If a star has low metallicity, there should be fewer solid materials available to form planetary cores, making the formation of gas giants unlikely. Yet, astronomers have discovered Jupiter-sized exoplanets orbiting stars with surprisingly low metal content. This challenges our theories of planet formation and suggests that alternative mechanisms, such as gravitational instabilities in the disk, may be more significant than we previously thought. Even more puzzling is the presence of metal-rich planets orbiting metal-poor stars. Some planets, known as super-Earths, appear to have compositions richer in heavy elements than their parent stars would suggest. This raises the possibility that planetary formation processes may not always reflect the metallicity of their host stars in a straightforward manner. Perhaps metals can accumulate in certain regions of a protoplanetary disk in ways that are not yet fully understood. The relationship between metallicity and planetary habitability is another area of intense study. Since elements like carbon, oxygen, and nitrogen are essential for life as we know it, the availability of these elements in a star system could influence the likelihood of life emerging. Some scientists have speculated that metal-rich environments may produce more complex chemistry, increasing the chances of biological evolution. However, too many metals could also lead to the formation of more gas giants and fewer habitable rocky planets, creating a delicate balance between metal abundance and the conditions necessary for life. Beyond planetary systems, the metallicity problem also ties into the broader question of how different types of galaxies evolve. Dwarf galaxies, for example, often exhibit strange metallicity distributions. Some contain pockets of extremely metal-poor gas, while others have regions that appear surprisingly enriched. This variation suggests that dwarf galaxies may experience metal enrichment in fits and starts rather than through a smooth, continuous process. One explanation for this uneven distribution is that dwarf galaxies have weaker gravitational fields, making it easier for supernova explosions to expel metals into intergalactic space. Unlike larger galaxies, which can hold on to their heavy elements and recycle them into new generations of stars, dwarf galaxies may lose much of their enriched material. This would explain why some regions remain metal-poor even after billions of years of evolution. Yet there are exceptions. Some dwarf galaxies show higher metallicities than expected, suggesting that they may have received an influx of enriched material from interactions with other galaxies. When larger galaxies pass near or merge with dwarf galaxies, they can transfer metal-rich gas, altering the chemical composition of the smaller galaxy. This process, known as galactic cannibalism, may be a key factor in shaping the metallicity profiles of smaller stellar systems. The metallicity problem also extends to the universe's most distant and ancient galaxies. Observations of galaxies billions of light-years away, meaning we see them as they were in the early universe, reveal surprisingly high levels of metals. According to our standard models of cosmic evolution, these galaxies should not have had enough time to generate such a high concentration of heavy elements. This suggests that metal enrichment in the early universe may have been far more rapid and efficient than we currently understand. One possibility is that the first generation of stars, population 3 stars, were much more massive and explosive than previously thought. If these stars burned through their fuel quickly and exploded in powerful supernovae, they could have enriched the surrounding gas much more rapidly than expected. This would help explain why some early galaxies appear to be more metal-rich than our models predict. However, no direct observations of population 3 stars have been made, leaving this theory unconfirmed. Another possibility is that massive black holes in the early universe played a role in accelerating metal enrichment. Supermassive black holes at the centers of young galaxies generate intense radiation and energetic outflows, which could stir up interstellar gas and promote rapid star formation. If this process also led to more efficient mixing of metals, it could explain the unexpected metallicity levels in ancient galaxies. The uneven distribution of metals across cosmic time raises deep questions about the nature of galaxy formation and evolution. Are metals distributed in a largely stochastic manner, governed by chaotic and unpredictable forces? Or is there an underlying pattern that we have yet to decipher? The answer may require a fundamental revision of our understanding of how the universe processes and recycles heavy elements. As we look ahead to the future of astrophysical research, new tools and technologies will play a crucial role in solving the metallicity problem. The James Webb Space Telescope, JWST, is already providing unprecedented insights into the early universe, allowing astronomers to study the formation of the first galaxies in greater detail. Upcoming missions like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, ELT, will further refine our ability to measure stellar compositions across vast cosmic distances. Simultaneously, advances in computational astrophysics will allow researchers to simulate metal enrichment processes with greater precision. By modeling the life cycles of stars, galaxies, and interstellar gas clouds, scientists may be able to identify previously unrecognized patterns in metal distribution. These simulations could reveal whether metallicity variations arise from fundamental physical processes or from random, chaotic events. The metallicity problem serves as a powerful reminder that the universe is far more complex than we often assume. Every discovery related to this mystery deepens our appreciation of the intricate and dynamic processes that govern the cosmos. From the formation of the first elements to the evolution of galaxies and the birth of planets, metallicity plays a crucial role in shaping the universe as we know it. Yet, despite all our progress, many questions remain unanswered. Why do some stars defy the expected metallicity patterns? How do metals migrate across vast cosmic distances? Could unknown forces, perhaps even interactions with dark matter, be influencing the chemical evolution of galaxies? These are the kinds of questions that push the boundaries of human knowledge and drive the relentless quest to understand the universe. As new discoveries emerge, one thing is certain: the metallicity problem is not just a minor technical issue, it is a gateway to some of the deepest and most profound mysteries of astrophysics. It challenges us to rethink our assumptions, refine our models, and embrace the unknown. The more we explore, the more we realize that the cosmos is an ever-evolving puzzle, filled with hidden clues waiting to be uncovered. The metallicity problem is not just a theoretical puzzle, it has profound implications for our understanding of cosmic history and the potential for life beyond Earth. By unraveling the complexities of metallicity distribution, we may gain deeper insights into how galaxies evolve, how stars form, and whether certain environments are more conducive to the emergence of habitable planets. One of the most intriguing aspects of this problem is its connection to the earliest moments of the universe. When the Big Bang occurred, it produced only hydrogen, helium, and trace amounts of lithium. All other elements, the heavy metals we now see in stars, planets, and even our own bodies, were forged in the hearts of stars through nuclear fusion and later dispersed through stellar explosions. This process, known as stellar nucleosynthesis, is the foundation of chemical evolution in the cosmos. However, the rate and efficiency of this enrichment process remain a mystery. Some regions of the universe appear to have accumulated metals much faster than others, and certain galaxies exhibit unexpected levels of chemical diversity. This raises fundamental questions. Did the first generations of stars behave differently than we expect? Were the earliest galaxies more efficient at producing heavy elements? Or could there be additional, yet undiscovered mechanisms contributing to metal distribution on cosmic scales? One potential explanation lies in the role of supernovae. When massive stars reach the end of their lives, they explode in powerful supernovae, releasing vast amounts of energy and newly formed elements into space. The intensity of these explosions can influence how metals are distributed across a galaxy. In some cases, supernovae may eject metals into intergalactic space, preventing them from being incorporated into new stars. In other cases, they may trigger waves of star formation, leading to rapid metal enrichment. Recent observations suggest that different types of supernovae contribute to metallicity in varying ways. Type Ia supernovae, which occur in binary star systems, produce large amounts of iron and other heavy elements. Core collapse supernovae, which result from the deaths of massive stars, contribute oxygen, carbon, and lighter metals. The balance between these two processes may play a crucial role in determining a galaxy's overall metal content. Another factor to consider is the influence of galactic mergers. When galaxies collide, their interstellar gas clouds mix, potentially altering their metallicity in unexpected ways. Some simulations suggest that mergers can lead to localized pockets of high metallicity, while other regions remain relatively untouched. This could help explain why some galaxies exhibit extreme chemical diversity within the same structure. Even within individual galaxies, metallicity is not evenly distributed. The Milky Way, for example, has a well-documented metallicity gradient, with metal-rich stars concentrated in the galactic core and metal-poor stars found in the outer halo. This suggests that star formation and metal recycling processes operate differently in different parts of a galaxy. The precise reasons for these variations remain an area of active research. The interplay between metallicity and dark matter is another intriguing aspect of this problem. Some studies have suggested that metal-poor regions of galaxies may be correlated with higher concentrations of dark matter. If true, this could imply a deeper connection between dark matter and the processes governing star formation and chemical evolution. However, the nature of dark matter remains elusive, making it difficult to determine whether these correlations are causal or coincidental. One of the most surprising discoveries in recent years is the existence of metal-free stars. These hypothetical objects, known as population 3 stars, are thought to have been the first stars to form in the universe. Because they lacked metals, they would have had unique physical properties, possibly growing to enormous sizes and burning at extreme temperatures. Although no confirmed population 3 stars have been observed, indirect evidence suggests they played a key role in the early enrichment of the cosmos. If population 3 stars were as massive as some models suggest, they would have lived fast and died young, exploding as hypernovae and dispersing heavy elements throughout the early universe. This could help explain why some ancient galaxies show higher than expected metallicity levels. However, without direct observations of these primordial stars, their exact impact remains speculative. Another fascinating aspect of metallicity is its influence on stellar lifespans. Metal-rich stars tend to be cooler and longer-lived than their metal-poor counterparts. This is because metals in a star's atmosphere can absorb radiation, slowing the rate at which energy escapes. As a result, high metallicity stars burn their fuel more slowly, potentially extending their lifespans by billions of years. Conversely, metal-poor stars are hotter and more luminous, meaning they burn through their fuel more quickly. This has implications for the search for habitable worlds, as it suggests that the environments around metal-poor stars may be more volatile and less stable over long timescales. Metallicity also plays a key role in the formation of planetary systems. As mentioned earlier, metal-rich stars are more likely to host giant planets, while metal-poor stars tend to have smaller, rocky planets. However, recent discoveries have challenged this assumption. Some metal-poor stars have been found to host gas giants, suggesting that alternative planet formation mechanisms may be at work. One possibility is that gas giants around metal-poor stars formed through gravitational instabilities rather than the traditional core accretion model. In this scenario, massive protoplanetary disks could collapse directly into gas giant planets without requiring a solid core. If true, this would mean that planets can form under a wider range of conditions than previously thought. Another mystery is the existence of ultra-metal-poor stars in the Milky Way. These stars have metallicities lower than any known galaxy, suggesting they may be relics from the early universe. Some researchers believe they could be remnants of ancient dwarf galaxies that were absorbed by the Milky Way billions of years ago. If so, studying them could provide a window into the chemical conditions of the cosmos's earliest epochs. Despite these mysteries, astronomers continue to make progress in understanding the metallicity problem. Large-scale surveys, such as the Gaia mission and the Sloan Digital Sky Survey, are mapping the metallicity of stars across the Milky Way in unprecedented detail. These observations are helping scientists reconstruct the history of our galaxy and refine models of stellar evolution. At the same time, new telescopes like the James Webb Space Telescope are allowing researchers to peer deeper into the cosmos than ever before. By studying the light from distant galaxies, astronomers can trace the evolution of metallicity across billions of years of cosmic history. These observations may ultimately reveal whether our current theories of chemical enrichment are correct, or if new physics is needed to explain the data. Ultimately, the metallicity problem is more than just a question of star composition. It is a fundamental challenge to our understanding of how the universe evolves. The distribution of metals shapes the formation of galaxies, influences the development of planetary systems, and even affects the potential for life. As we continue to explore this cosmic enigma, we may uncover new insights that reshape our understanding of the universe itself. Another key aspect of the metallicity problem is its connection to galactic evolution and the overall structure of the universe. The metallicity of a galaxy is a direct consequence of its history, how many generations of stars have lived and died within it, how efficiently it has retained heavy elements, and how it has interacted with other galaxies over cosmic time. By analyzing metallicity trends across different types of galaxies, astronomers can piece together a more complete picture of how the universe has evolved. One of the most striking findings from large-scale surveys is that metallicity tends to increase over time. This makes sense when considering the cycle of stellar birth and death. When a new generation of stars forms, it incorporates the metals produced by previous generations, leading to a gradual buildup of heavier elements. However, this process does not happen at the same rate everywhere. Some galaxies show a much slower buildup of metals, while others have inexplicably high metallicity levels, challenging our understanding of how metal enrichment works. For example, dwarf galaxies often have significantly lower metallicity compared to larger spiral or elliptical galaxies. This is partly because dwarf galaxies have weaker gravitational fields, making it easier for supernovae to expel metal-rich gas into intergalactic space. As a result, many dwarf galaxies have remained chemically primitive, preserving conditions similar to those found in the early universe. Studying these galaxies provides valuable clues about how the first generations of stars might have formed and evolved. On the other hand, some high metallicity galaxies appear to have undergone rapid periods of star formation, leading to intense metal enrichment. These galaxies may have experienced major mergers or bursts of supernova activity, which accelerated their chemical evolution. The existence of such galaxies suggests that metal enrichment is not always a gradual process but can instead occur in dramatic, unpredictable bursts. Another challenge in understanding the metallicity problem comes from the intergalactic medium, the vast expanse of gas between galaxies. When a galaxy ejects metal-rich material through supernova explosions or galactic winds, some of those metals escape into intergalactic space. Over billions of years, this process has enriched the intergalactic medium with heavier elements. However, recent observations suggest that the amount of metals in intergalactic space is lower than expected, implying that we may be missing key aspects of how metals are transported and retained within galaxies. One hypothesis is that magnetic fields and cosmic rays play a role in regulating the movement of metals. These forces could help confine metal-rich gas within galaxies, preventing it from escaping into intergalactic space. Alternatively, there may be yet undiscovered mechanisms that allow metals to mix more efficiently across cosmic scales. Understanding how metals move through the universe is crucial for refining models of galaxy formation and evolution. Another unresolved question is why some ancient stars in the Milky Way exhibit unexpectedly high metallicity. These stars, found in the galactic halo and globular clusters, should be relics from the early universe when metals were scarce. Yet, some of them contain elements that should have taken billions of years to accumulate. This raises the possibility that these stars may have formed in environments with unusual metal enrichment histories, possibly influenced by the explosions of early supermassive stars or exotic astrophysical processes. The discovery of metal-poor exoplanets has also added a new layer of complexity to the metallicity problem. Traditionally, it was believed that planets were more likely to form around metal-rich stars, as metals are essential for building solid planetary cores. However, astronomers have found several exoplanets orbiting extremely metal-poor stars, challenging this assumption. This suggests that planet formation may be more diverse than previously thought, with alternative pathways allowing planets to emerge even in environments with minimal heavy elements. One potential explanation is that these planets formed in metal-rich pockets within otherwise metal-poor regions. Another possibility is that some planets may have formed through gravitational instabilities rather than the slow accumulation of solid material. If confirmed, this would have profound implications for the search for habitable worlds, as it would mean that potentially life-bearing planets could exist in a wider range of stellar environments than previously believed. The metallicity problem also has implications for our understanding of cosmic inflation and the early universe. Some theories suggest that variations in metallicity could be linked to the distribution of dark matter, which played a crucial role in shaping the large-scale structure of the universe. If metallicity variations are influenced by dark matter, this could provide indirect evidence for how dark matter interacts with ordinary matter, a major unsolved mystery in astrophysics. Additionally, understanding metallicity is crucial for refining models of stellar evolution. The presence of metals affects nearly every aspect of a star's life cycle, from how it forms to how it burns fuel and ultimately how it dies. Stars with higher metallicity tend to be cooler and have stronger stellar winds, while metal-poor stars burn hotter and live shorter lives. These differences have cascading effects on everything from the formation of planetary systems to the types of supernovae that occur in different regions of the universe. The role of metallicity in black hole formation is another area of active research. Recent studies suggest that metal-poor stars are more likely to collapse directly into black holes rather than exploding as supernovae. This means that regions with lower metallicity may be prime locations for the formation of massive black holes, which could help explain the rapid growth of supermassive black holes in the early universe. Understanding these processes is key to solving one of the biggest questions in astrophysics. How did the first black holes grow so large, so quickly? One of the most promising avenues for addressing the metallicity problem is the study of extremely distant galaxies. Thanks to advances in telescopes like the James Webb Space Telescope, astronomers can now observe galaxies from the earliest epochs of cosmic history. By measuring the metallicity of these ancient galaxies, scientists can test predictions about how quickly metals were produced in the early universe. Some early results suggest that the first galaxies may have been more chemically evolved than previously expected. If confirmed, this would challenge existing models of star formation and chemical evolution, possibly requiring revisions to our understanding of the early universe. On the other hand, if these galaxies are found to be nearly metal-free, this would support the idea that the first generations of stars were truly unique, with physical properties unlike anything seen in the modern universe. Ultimately, the metallicity problem is a gateway to deeper questions about the nature of the cosmos. It ties together multiple areas of astrophysics, from galaxy evolution and stellar life cycles to dark matter and cosmic inflation. As our observational capabilities continue to improve, new discoveries will likely shed light on the processes that govern the distribution of elements in the universe. Yet, for every question we answer, new mysteries emerge. Why do some regions of the universe appear to have been enriched with metals far earlier than expected? What mechanisms regulate the movement of metals between galaxies? And could there be entirely new physics at play that we have yet to uncover? As we look to the future, missions like the Vera C. Rubin Observatory and upcoming space telescopes will provide even more detailed maps of the universe's chemical composition. These data will help astronomers refine models of how stars and galaxies evolve over billions of years. But for now, the metallicity problem remains one of the most perplexing mysteries in astrophysics, a reminder that the universe still holds secrets waiting to be unlocked. The metallicity problem is more than just a puzzle about how much metal is in a star. It's a fundamental issue that connects to the evolution of the universe itself. One of the most baffling aspects of this problem is the presence of metal-poor stars in regions where we would expect much higher metallicity. These ancient stars, sometimes called population 2 or even population 3 candidates, seem to contradict the expected timeline of metal enrichment. If metals were steadily building up over time, then why do some stars, even ones in the Milky Way's halo, have metal levels that suggest they formed billions of years ago in nearly pristine conditions? One theory suggests that these stars may have originated outside of the Milky Way and were later captured through galactic mergers. If a small, metal-poor dwarf galaxy was absorbed into the Milky Way billions of years ago, its stars could have been scattered throughout the halo, creating a mixed population with widely varying metallicities. This explanation is supported by the discovery of stellar streams, long, faint trails of stars that suggest past galactic mergers. These streams contain stars with unusual chemical compositions, further hinting at a complex history of stellar migration. However, some stars defy even this explanation. Certain ultra-metal-poor stars appear to have formed in the Milky Way itself, rather than being immigrants from smaller galaxies. These stars have chemical signatures that suggest they were enriched by only one or two supernova explosions, meaning they must be among the first stars to have formed in our galaxy. But their mere existence poses a question: how did they manage to survive for billions of years without accumulating additional metals? One possibility is that these stars formed in isolated pockets of gas that remained metal-poor even as the rest of the galaxy evolved. If these pockets were shielded from the influence of later generations of stars, they could have retained their primitive chemical makeup. Another possibility is that the first supernovae in the galaxy distributed metals in a much more uneven way than previously thought, creating localized regions with vastly different compositions. Recent research has also revealed an unexpected relationship between metallicity and stellar rotation. Some studies suggest that metal-poor stars tend to rotate faster than their metal-rich counterparts. This could be due to differences in their formation process, perhaps lower metallicity allows for less efficient angular momentum loss, leading to faster spinning stars. If true, this could have implications for everything from stellar evolution models to the formation of neutron stars and black holes. The metallicity problem also has profound implications for cosmology. The cosmic microwave background (CMB) provides a snapshot of the universe when it was only about 380,000 years old, long before stars began forming. By studying the CMB, scientists can estimate how much normal matter, as opposed to dark matter or dark energy, was present in the early universe. This, in turn, should allow them to predict how quickly metals should have built up over time. But when astronomers compare these predictions with actual observations of metal-rich and metal-poor stars, inconsistencies arise. If metal enrichment happened too quickly, it could mean that early star formation was much more intense than expected. On the other hand, if there are more metal-poor stars than predicted, it might suggest that some unknown process slowed down early metal production. One possible explanation is that some of the first stars were much more massive than previously thought, exploding as hypernovae that distributed metals in a very different pattern than ordinary supernovae. The study of ancient quasars, supermassive black holes at the centers of early galaxies, has added another layer of complexity to the metallicity problem. Quasars are among the brightest objects in the universe, allowing astronomers to study their spectra and determine the composition of gas in the early cosmos. Surprisingly, some quasars from just a few 100 million years after the Big Bang already show evidence of significant metal enrichment. This suggests that the first generations of stars must have lived and died incredibly fast, rapidly producing metals and enriching their surroundings far earlier than expected. This leads to yet another mystery. If early metal enrichment was so rapid, why do we still find pockets of extremely metal-poor gas in the modern universe? Some regions of intergalactic space appear to have remained chemically pristine for billions of years, untouched by the cycle of star formation and destruction. This challenges our understanding of how metals spread through cosmic structures and raises questions about the efficiency of galactic winds, supernova feedback, and intergalactic magnetic fields. One possible answer involves the large-scale structure of the universe itself. Galaxies are not distributed randomly. They form along vast cosmic filaments, with enormous voids in between. These voids could act as reservoirs of nearly pristine gas, preserving conditions similar to those found in the very early universe. If true, this would suggest that metal enrichment has been highly uneven, with some regions evolving rapidly while others have remained frozen in time. The role of metallicity in planet formation is another aspect of the problem that continues to challenge astronomers. Traditionally, it was believed that metal-rich stars were more likely to host planets, since heavy elements are essential for forming solid planetary cores. However, the discovery of gas giants around extremely metal-poor stars has forced a re-evaluation of this idea. Some of these planets may have formed through gravitational instabilities rather than the traditional core accretion model, meaning that planet formation could be more diverse than previously assumed. Additionally, metallicity affects the composition of planetary atmospheres, which has major implications for the search for habitable worlds. Planets around metal-poor stars may have very different atmospheric chemistry compared to Earth, potentially influencing their ability to support life. Some researchers have even suggested that the habitability of a planet could depend not just on its position relative to its star but also on the star's metallicity, which could influence everything from atmospheric retention to the availability of key elements like carbon, nitrogen, and oxygen. As our observational capabilities continue to improve, new discoveries will likely refine our understanding of the metallicity problem. The James Webb Space Telescope has already begun revealing new insights into the composition of some of the earliest galaxies, while upcoming missions like the European Space Agency's Plato, planetary transits and oscillations of stars, will provide a deeper understanding of stellar and planetary metallicity. But for now, the metallicity problem remains an open question, a reminder that even the most fundamental aspects of the universe, like the distribution of its basic elements, are still not fully understood. Every new discovery adds another piece to the puzzle, but at the same time, it often raises new questions that challenge our existing theories. The universe, it seems, is always more complex than we expect, and the deeper we look, the more mysteries we uncover. The metallicity problem is a window into the complex interplay between stellar evolution, galactic formation, and the fundamental forces shaping the cosmos. While we have discussed the anomalies of metal-poor stars, stellar migration, and the unexpected enrichment of early quasars, there are even deeper implications that extend into dark matter interactions, the formation of exotic stellar objects, and the potential existence of undiscovered astrophysical processes. One of the most intriguing connections between metallicity and cosmology is its potential link to dark matter. Dark matter remains one of the greatest unsolved mysteries in physics, yet its gravitational influence is unmistakable in the formation of galaxies. If dark matter played a role in the early clustering of stars, it may have influenced metallicity distribution in ways we have yet to fully understand. Some models suggest that dark matter could affect the cooling of primordial gas, impacting the formation of the first stars and, consequently, the rate of metal enrichment. If this is true, then metallicity anomalies could be indirect evidence of dark matter's role in cosmic evolution. Another possibility is that the first generation of stars, the hypothetical population 3 stars, did not form in the way we expect. These stars, theoretically composed of pure hydrogen and helium, should have burned through their fuel rapidly and ended their lives in massive supernovae, enriching the universe with heavy elements. However, if some of these stars managed to survive in unexpected ways, perhaps as exotic remnants or even as long-lived, dim objects that have eluded detection, it could explain why certain regions remain metal-poor. Recent observations have also suggested the presence of superluminous supernovae, explosions that far exceed the brightness of typical stellar deaths. These could be the remnants of population 3 stars, but if they were more common than anticipated, they could have led to highly uneven metal distribution, creating metal-rich pockets while leaving vast regions untouched. This could explain why metal-poor stars persist even in locations where we would expect enrichment to be widespread. There is also the question of whether metallicity influences the nature of black holes. In conventional astrophysics, metal-rich stars tend to lose more mass through stellar winds before collapsing, potentially leading to lower-mass black holes. In contrast, metal-poor stars retain more of their mass, making them more likely to form the heavy black holes observed in gravitational wave detections. The LIGO and Virgo observatories have recorded black hole mergers involving objects much more massive than those expected from typical stellar evolution. If these black holes originated from metal-poor stars, it suggests that early stellar populations might have been far more diverse than we anticipated. Furthermore, the metallicity problem raises significant questions about the life cycle of galaxies. Some of the most metal-poor stars are found in the outskirts of galaxies, suggesting that these stars either migrated outward or formed in isolated conditions. If metallicity is not evenly distributed, it implies that our understanding of galactic chemical evolution may need revision. It is possible that different regions of a galaxy experience separate waves of star formation, leading to isolated pockets of metal-poor and metal-rich material that still persist today. This could also explain the unusual nature of globular clusters, dense groups of ancient stars that often contain a strange mix of metallicities. Some globular clusters appear to host multiple generations of stars, indicating that they may have experienced complex histories involving mergers or interactions with other galactic structures. However, other clusters remain stubbornly metal-poor, as if frozen in time from the early universe. Understanding these clusters could provide crucial insights into how metals were distributed throughout cosmic history. Even more puzzling is the role of interstellar and intergalactic gas in the metallicity problem. If metals were created in supernovae and dispersed by stellar winds, then why do some regions of space remain largely untouched by these elements? Some theories suggest that powerful galactic winds might have expelled metals into intergalactic space, creating a hidden reservoir of heavy elements that we have yet to detect. Others propose that certain mechanisms, such as magnetic fields or feedback loops from active galactic nuclei, could have prevented metals from spreading uniformly. In recent years, astronomers have also turned to high-redshift galaxies, those seen at extreme distances, representing an earlier time in the universe's history, to study metallicity evolution. Surprisingly, some of these ancient galaxies already show signs of significant metal enrichment, suggesting that early star formation was far more efficient than expected. If this is true, it could mean that the first stars and galaxies were much more dynamic than our current models predict, rapidly synthesizing metals and distributing them across vast cosmic distances. Yet, paradoxically, other galaxies appear to be metal deficient, as if they formed in isolation from the broader cosmic network. This raises the possibility that large-scale cosmic structures, such as filaments and voids, played a major role in determining where metals accumulated. If some regions of space were more favorable for rapid metal enrichment, while others remained chemically stagnant, it could mean that our understanding of galaxy formation is missing a crucial piece of the puzzle. Another unexplored aspect of the metallicity problem is how it might influence exotic forms of life. While we often think of carbon, oxygen, and nitrogen as essential building blocks for life, it is possible that alien biochemistries could depend on entirely different elements. If metallicity influences planetary composition, then planets in metal-poor regions may have drastically different chemical environments, potentially supporting forms of life that are unlike anything we have encountered. There is also the question of how metallicity affects the habitability of a galaxy itself. Some astronomers have proposed the idea of a galactic habitable zone, a region where conditions are optimal for life to develop. If metals play a crucial role in planetary formation, then galaxies with higher metallicity may have more planets capable of supporting complex ecosystems. On the other hand, galaxies with extremely low metallicity might be barren, with fewer solid planets and a lower likelihood of life emerging. As observational technology continues to improve, we will likely gain new insights into the metallicity problem. The upcoming Extremely Large Telescope, ELT, and the Vera-C Rubin Observatory will provide unprecedented views of distant stars and galaxies, allowing astronomers to map metal distribution across cosmic time with greater accuracy. Meanwhile, next-generation space telescopes will analyze the atmospheres of exoplanets, shedding light on how metallicity influences planetary environments. But for now, the mystery remains unsolved. The universe is filled with anomalies, contradictions, and unexpected discoveries that challenge our understanding of how the cosmos evolved. The metallicity problem is not just about stars, it is a question that touches on the very fabric of reality, linking together astrophysics, cosmology, and the search for life beyond Earth. It is a reminder that science is an ongoing process, where every answer leads to new questions, and every mystery reveals an even deeper puzzle waiting to be explored. The metallicity problem continues to pose profound challenges to our understanding of the universe, not just in terms of stellar formation and galactic evolution but also in the fundamental physics that govern the cosmos. One of the most perplexing aspects of this issue is how certain stars and galaxies appear to defy the expected trends of metal enrichment. Why do some metal-poor stars exist in locations where they shouldn't? Why do some distant galaxies exhibit metal content that seems inconsistent with their age? These questions lead us deeper into the heart of astrophysical mysteries, forcing us to reconsider our models of how elements spread across the universe. One particularly strange aspect of the metallicity problem is the existence of metal-poor stars in environments that should be metal-rich. The Milky Way, for example, contains a population of ancient, metal-poor stars that exist within its disk, a region that should have been well enriched with heavier elements over billions of years. This raises the question, how did these stars end up there? One possible explanation is stellar migration. These stars may have formed in metal-poor environments, such as dwarf galaxies, and later been pulled into the Milky Way through gravitational interactions. However, this still doesn't explain why some stars show even more extreme metal deficiencies than expected, suggesting that some of these objects might have an entirely different origin. Another fascinating aspect of the metallicity problem is the role of supernovae in distributing heavy elements. Supernova explosions are responsible for forging many of the heavier elements in the universe, scattering them into space to eventually be incorporated into new stars and planets. However, observations of certain ancient galaxies suggest that metal enrichment did not occur as uniformly as expected. Some regions appear to have been heavily enriched, while others remain strangely metal-poor, hinting at complex feedback mechanisms that may have prevented metals from spreading evenly. Some scientists speculate that early galaxies may have experienced violent, rapid bursts of star formation followed by long periods of inactivity, leading to uneven metal distribution. An even more perplexing observation comes from distant quasars, massive, active galaxies powered by supermassive black holes at their centers. Some of these quasars, which date back to the early universe, show evidence of surprisingly high metallicity, contradicting the expectation that the first galaxies should have been metal poor. If metals take time to accumulate, then how did these galaxies become so enriched in just a few 100 million years after the Big Bang? This suggests that either star formation and supernova feedback were far more efficient in the early universe than we thought, or that some unknown mechanism accelerated metal production on cosmic scales. This problem extends to globular clusters as well, ancient, tightly bound groups of stars that orbit galaxies. Many globular clusters contain stars with a wide range of metallicities, indicating that these clusters may have undergone multiple waves of star formation rather than forming all at once, as previously believed. However, some clusters remain entirely metal poor, as if they were frozen in time from the earliest epochs of the universe. Understanding these clusters could provide key insights into how metals were distributed throughout cosmic history. One particularly bizarre implication of the metallicity problem involves the formation of black holes. Observations from gravitational wave detectors such as LIGO and Virgo have revealed the existence of black hole mergers involving objects far more massive than expected. One leading explanation is that these black holes formed from metal-poor stars, which lose less mass through stellar winds before collapsing, allowing them to retain more of their original bulk. If this is the case, it suggests that metal-poor environments might be prime locations for producing heavy black holes, fundamentally altering our expectations about where such objects should be found. In addition to black holes, metallicity could also influence the formation of neutron stars and even exotic hypothetical objects such as quark stars or boson stars. If metals affect the way matter collapses under extreme gravity, then understanding metallicity distribution could be crucial to predicting where different types of compact objects exist in the universe. Some neutron stars, for example, exhibit strange magnetic properties and rotational behaviors that suggest they may have formed in environments with unusual metallicity conditions. Metallicity may even play a role in the nature of dark matter itself. Some theories suggest that dark matter could interact with ordinary matter in subtle ways that influence star formation and metal distribution. If dark matter has any effect on the cooling of primordial gas, then it could have shaped the first generations of stars, altering their metallicity in ways we do not yet understand. This raises the possibility that metallicity anomalies could be indirect evidence of dark matter's influence on cosmic structure. Another curious link between metallicity and cosmology involves the large-scale structure of the universe. Observations suggest that galaxies are not distributed randomly but instead follow a web-like structure known as the cosmic web, with vast filaments of galaxies separated by enormous voids. If metal enrichment occurred differently in different parts of the universe, then some of these voids may have remained metal-poor due to inefficient star formation. This could mean that entire regions of the cosmos are fundamentally different in composition from others, challenging the assumption that the universe is homogeneous on large scales. Even on a smaller scale, metallicity has profound implications for the search for extraterrestrial life. The chemical composition of a planet is heavily influenced by the metallicity of its parent star, meaning that planets around metal-poor stars may have vastly different elemental makeups. If life depends on certain heavy elements, then metal-rich regions of the galaxy may be more favorable for habitability, while metal-poor regions might be barren. However, it is also possible that life could emerge in unexpected ways, using alternative chemical pathways that do not rely on traditional biochemistry. As we continue to explore exoplanets, studying the relationship between stellar metallicity and planetary formation could help us determine which systems are most likely to host life. Future space telescopes, such as the James Webb Space Telescope and its successors, will be able to analyze the atmospheres of exoplanets in unprecedented detail, providing crucial data on how metallicity shapes planetary environments. Ultimately, the metallicity problem is not just about stars. It is a puzzle that connects nearly every aspect of astrophysics, from the formation of the first elements to the structure of galaxies, the nature of black holes, and the search for life beyond Earth. As technology advances, we will likely uncover even more surprising insights into the cosmic distribution of metals, forcing us to rethink our fundamental understanding of the universe. The more we learn, the more we realize how much remains unknown, and the deeper we go, the more mysteries we uncover. The metallicity problem forces us to reconsider long-standing assumptions about how the universe evolved over billions of years. If metals are formed by successive generations of stars, then why do some stars and galaxies exhibit metal content that contradicts this gradual enrichment process? The deeper we investigate, the more anomalies we find, suggesting that metallicity is influenced by far more than just stellar evolution alone. This problem extends beyond individual stars and galaxies and touches on the fundamental forces that shape the cosmos, from the earliest moments after the Big Bang to the current structure of the universe. One of the most perplexing questions about metallicity is why some stars appear to have formed from nearly pristine gas, seemingly untouched by previous generations of supernovae. In theory, the earliest stars, known as population 3 stars, should have been entirely devoid of heavy elements, forming from pure hydrogen and helium left over from the Big Bang. These stars should have been incredibly massive, burning quickly and exploding as supernovae, enriching the surrounding gas with metals that would later contribute to the formation of population 2 and population 1 stars. However, astronomers have never directly observed a population 3 star. Instead, they have discovered stars that are almost metal-free but not completely, meaning that some unknown process must have introduced trace amounts of metals even in the earliest epochs of star formation. This raises a profound question: were population 3 stars truly the first stars in the universe, or did another mechanism contribute to early metal enrichment? Some astrophysicists propose that tiny amounts of heavy elements may have been produced in unexpected ways, such as through exotic forms of nucleosynthesis occurring in the aftermath of the Big Bang, or even through interactions with dark matter. If true, this would mean that the first stars were not as pristine as previously thought, challenging our understanding of how the first galaxies formed. The mystery deepens when we examine the distribution of metallicity in galaxies across cosmic time. Surveys of distant galaxies reveal that while some early galaxies are rich in metals, others remain surprisingly metal-poor, even billions of years after the first supernovae exploded. This suggests that the process of metal enrichment is not uniform and that some galaxies have managed to remain isolated from the heavy element recycling process. How could this happen? One possibility is that some galaxies formed in cosmic voids, vast, empty regions of space where the density of matter is extremely low. In these isolated pockets, fewer stars would have formed, and metals would have taken longer to accumulate. But another, even stranger possibility is that some galaxies have experienced massive metal loss. High-energy processes such as supernova-driven winds and active galactic nuclei, AGN, outflows can eject metals into intergalactic space, stripping galaxies of their heavy elements and leaving behind metal-poor stellar populations. In extreme cases, entire galaxies may have lost most of their metals to the vast emptiness of space, leading to a scenario where metals exist in the cosmic medium rather than within galaxies themselves. If so, this could mean that much of the metal content of the universe is not found within stars or planets, but instead dispersed throughout intergalactic space, hidden from traditional observational methods. This also ties into another peculiar observation. Why do some dwarf galaxies contain higher metallicity than expected while some massive galaxies have metal-poor regions? Traditionally, astronomers expected that larger galaxies, with their deeper gravitational wells, should retain metals more effectively than small dwarf galaxies. However, some small galaxies have been found to be more metal-rich than their massive counterparts. One possible explanation is that dwarf galaxies can sometimes undergo periods of intense star formation known as starbursts, rapidly enriching their gas with heavy elements. Alternatively, interactions with nearby galaxies may lead to metal mixing, where gas flows between galaxies redistribute elements in unexpected ways. One particularly intriguing case of metallicity anomalies comes from studies of the Andromeda Galaxy, our closest galactic neighbor. Observations of Andromeda's stellar halo, a vast region surrounding the main disk, reveal stars with an extremely broad range of metallicities, far more diverse than what is found in the Milky Way's halo. This suggests that Andromeda has undergone a more chaotic history of mergers and accretions, incorporating stars from multiple metal-rich and metal-poor progenitor galaxies. If true, this implies that the metallicity of a galaxy is not just determined by its internal processes, but also by its history of interactions with other galaxies. This brings us to another major question: what role does metallicity play in galaxy evolution over cosmic time? Metal-rich galaxies tend to have more active star formation, as metals help cool gas, allowing it to collapse into new stars more efficiently. However, at the same time, too many metals can alter the chemistry of gas clouds in ways that suppress star formation. This means that metallicity can act as both a driver and a regulator of galactic evolution, creating a delicate balance that shapes the way galaxies grow. Further complicating the issue is the fact that metallicity is not just a property of stars and galaxies. It also affects planetary systems and the potential for life. Studies of exoplanets have shown that metal-rich stars are more likely to host planets, especially gas giants like Jupiter and Saturn. This is because planet formation depends on the presence of solid materials like silicon, iron, and carbon, which require metals to exist. In metal-poor systems, there may not be enough heavy elements to form Earth-like planets, raising the possibility that some regions of the universe are less likely to host life simply because they lack the necessary building blocks. However, the relationship between metallicity and habitability is not straightforward. Some researchers suggest that very high metallicity might actually be detrimental to life, as it could lead to an overabundance of gas giants that disrupt the formation of smaller, rocky planets. Additionally, metal-rich stars tend to be more active and emit higher levels of radiation, which could pose challenges for life on nearby planets. This means that the ideal conditions for life may require a sweet spot of metallicity, either too low nor too high, raising the question of whether our solar system occupies a unique position in the metallicity spectrum. Looking even further, metallicity could influence the fate of the universe itself. Some cosmological models suggest that the long-term evolution of galaxies depends on how efficiently metals are retained or lost over billions of years. If metals are gradually lost to intergalactic space, then future generations of stars may become increasingly metal-poor, potentially altering the cycle of stellar evolution in ways we do not yet understand. In a far-future scenario, the universe might enter a state where metal production slows dramatically, changing the fundamental nature of cosmic evolution. Ultimately, the metallicity problem is not just about explaining the composition of stars. It is a deep and far-reaching mystery that ties into almost every aspect of astrophysics. From the earliest moments of the universe to the formation of planets and the potential for life, metallicity influences the structure and fate of the cosmos in ways we are only beginning to comprehend. As new telescopes and space missions provide more detailed data, we may finally unravel the secrets of metallicity, and in doing so, gain a deeper understanding of how the universe came to be. Yet, for all the progress we have made, the metallicity problem remains one of the most perplexing unsolved mysteries in astronomy. It forces us to question our assumptions, refine our models, and explore new frontiers in physics and cosmology. The more we uncover, the more we realize that the universe is far stranger and more complex than we ever imagined. Perhaps, in the coming decades, as our observational tools grow more advanced, we will finally solve the riddle of why some stars are so strange, and in doing so, we may unlock some of the deepest secrets of the cosmos. The metallicity problem is more than just an astrophysical curiosity. It is a fundamental challenge to our understanding of cosmic history, stellar evolution, and the mechanisms that shape galaxies. The deeper we dig into the enigma of metallicity, the more contradictions we uncover, suggesting that something crucial is still missing from our models. This issue does not just apply to individual stars, but also to entire galaxies, cosmic structures, and possibly even the evolution of life itself. One of the key mysteries in this puzzle is the apparent inconsistency in how metals are distributed across the universe. If heavy elements are produced through stellar nucleosynthesis and distributed by supernova explosions, we would expect to see a relatively even spread of metals across different regions of space. Instead, what we observe is a patchwork of extreme variations. Some galaxies and stars are surprisingly metal-poor, while others are unexpectedly metal-rich. This raises the question, why are metals so unevenly distributed, and what processes are responsible for these anomalies? One possible explanation involves the violent and chaotic nature of galactic evolution. Galaxies are not isolated entities. They interact, merge, and exchange material in ways that can dramatically alter their metallicity. Some galaxies undergo frequent mergers, mixing their metal content, while others remain relatively untouched for billions of years, preserving ancient, low-metallicity gas. This explains why some dwarf galaxies exhibit unexpectedly high metallicity. They may have stolen enriched gas from larger galaxies through gravitational interactions. On the other hand, some massive galaxies appear metal-poor because they have ejected much of their metal-rich gas into intergalactic space through powerful outflows driven by supernovae and active galactic nuclei, AGN. The role of AGN in metal distribution is particularly intriguing. Supermassive black holes at the centers of galaxies can produce intense radiation and particle jets that drive metals outward, expelling them from their host galaxies. In extreme cases, this process can lead to a situation where a galaxy retains very little of its own heavy elements, instead dispersing them into the cosmic void. Observations of distant galaxies have shown that some of the most powerful AGN-driven outflows are capable of ejecting metals at speeds exceeding thousands of kilometers per second, effectively preventing them from participating in future star formation. This brings up an even stranger question: where do these lost metals go? If galaxies are constantly shedding their heavy elements, we should expect to find a significant amount of metal enrichment in the intergalactic medium, IGM, the vast space between galaxies. Indeed, observations using X-ray telescopes have revealed that the IGM contains a surprising amount of metals, suggesting that the universe's heavy elements are not just confined to stars and planets, but are instead spread out across vast cosmic scales. However, even this does not fully account for the missing metals, leading to speculation that some metals may be locked away in unseen reservoirs such as cold gas clouds or even exotic forms of dark matter interactions. Another key aspect of the metallicity problem is how it influences the formation of planets. In general, high metallicity stars are more likely to host planetary systems, particularly gas giants like Jupiter and Saturn. This is because metals are essential for the formation of solid planetary cores, which then accumulate gas to form massive planets. However, the relationship between metallicity and planetary formation is complex. Too much metal enrichment can lead to an overabundance of gas giants, while too little metallicity may prevent planets from forming at all. Recent exoplanet surveys have shown that some metal-poor stars still manage to host planets, challenging the assumption that high metallicity is a strict requirement for planetary formation. Some astronomers propose that alternative mechanisms, such as gravitational instabilities in protoplanetary disks, may allow planets to form even in metal-poor environments. If true, this would mean that habitable planets could exist in regions of the universe that were previously thought to be barren. But what about life? Could metallicity influence the likelihood of biological evolution? Some researchers argue that the availability of certain heavy elements, such as iron, phosphorus, and zinc, plays a crucial role in the chemistry of life. If these elements are rare in a given stellar system, it might limit the potential for complex biological processes to emerge. On the other hand, very high metallicity could also pose challenges for life by increasing stellar activity and radiation exposure, potentially making some planets less hospitable. This leads us to a profound question: does the universe have a Goldilocks zone of metallicity for life? If there is an optimal range of metallicity that favors both planet formation and biological evolution, then our own solar system may be unusually well positioned within this range. The fact that our Sun has a moderate metallicity, either too high nor too low, may not be a coincidence, but rather a key factor in why life exists here. As we look further into the cosmos, we also begin to wonder whether metallicity affects the ultimate fate of the universe. If the long-term evolution of galaxies depends on how efficiently metals are retained or lost, then the future of star formation could be influenced by metallicity in ways we do not yet fully understand. Some theoretical models suggest that if metals continue to be ejected into intergalactic space, future generations of stars may become increasingly metal-poor, potentially altering the cycle of stellar evolution and changing the nature of the cosmos itself. The metallicity problem challenges everything we thought we knew about the universe. It forces us to reconsider the mechanisms that drive cosmic evolution, from the earliest stars to the formation of planets and the potential for life. It suggests that the distribution of heavy elements is not as simple as we once believed, and that hidden processes, whether they be unknown physics, exotic cosmic interactions, or yet undiscovered astrophysical mechanisms, may be at work. Despite all the progress we have made in understanding metallicity, the puzzle remains far from solved. Observations from next-generation telescopes, such as the James Webb Space Telescope, JWST, may provide new insights into the metal content of the earliest galaxies, shedding light on how the first stars contributed to cosmic chemical enrichment. Likewise, upcoming missions focused on exoplanetary atmospheres may reveal how metallicity influences habitability beyond our solar system. The deeper we investigate, the more mysteries we uncover, proving once again that the cosmos is far more complex and fascinating than we ever imagined. The metallicity problem is not just an issue of astrophysics. It is a window into the very fabric of the universe, offering tantalizing clues about how everything we see came to be. The quest to solve it is far from over, and in the process, we may rewrite the very story of the cosmos itself. The metallicity problem continues to challenge our understanding of how elements are distributed throughout the cosmos. As we dig deeper into this mystery, we begin to see how metallicity influences not only stars but entire galaxies, interstellar gas clouds, and even the fundamental physics governing cosmic evolution. It is a puzzle with far-reaching consequences, extending from the birth of the first stars to the potential fate of the universe itself. One of the most perplexing aspects of this problem is how metallicity appears to be linked to the formation of different types of galaxies. Observations show that smaller dwarf galaxies tend to have lower metallicity than larger spiral and elliptical galaxies. This makes sense in the context of stellar evolution. Dwarf galaxies have undergone fewer generations of star formation, meaning they have had less time to build up heavy elements. However, this pattern is not absolute. Some dwarf galaxies exhibit unexpectedly high metallicity, while certain massive galaxies are surprisingly metal-poor. This inconsistency suggests that external factors, such as galaxy mergers, supernova-driven outflows, and interactions with the intergalactic medium, are influencing metal distribution in ways we do not yet fully understand. Supernova explosions play a crucial role in the enrichment of galaxies, but their impact is not uniform. The most powerful supernovae, known as hypernovae, can expel heavy elements at such high velocities that they escape their host galaxy entirely, enriching the surrounding intergalactic medium rather than recycling metals into new stars. This means that some galaxies may become metal-poor not because they failed to produce metals, but because they lost them due to powerful stellar explosions. This could explain why some massive galaxies have lower than expected metallicity, as their supernovae have been efficient at ejecting metals beyond their gravitational reach. The presence of active galactic nuclei, AGN, adds another layer of complexity. Supermassive black holes at the centers of galaxies generate enormous amounts of energy, often producing high-speed jets and winds that can strip galaxies of their metal-rich gas. In extreme cases, AGN-driven outflows can remove so much material that star formation is effectively shut down, leaving behind a galaxy that is both metal-poor and inactive. This process, known as quenching, is believed to be responsible for the existence of red and dead elliptical galaxies that no longer form new stars. However, the effects of AGN are not entirely negative. Some models suggest that AGN-driven winds can also trigger star formation by compressing gas clouds, leading to localized bursts of metallicity enrichment. This dual role, both destroying and stimulating star formation, adds another layer of complexity to the metallicity problem, as it implies that the same mechanism can produce wildly different outcomes depending on a galaxy's mass, structure, and environment. Beyond galaxies, the intergalactic medium, IGM, presents another mystery. We know that vast amounts of heavy elements exist between galaxies, but how they got there is still unclear. The simplest explanation is that they were ejected by powerful galactic winds and supernovae. But the observed metallicity of the IGM does not match what we would expect from these processes alone. Some theories propose that an unknown mechanism, possibly involving cosmic filaments, long, thread-like structures of dark matter and gas that connect galaxies, plays a role in redistributing metals across cosmic distances. This brings us to one of the most speculative but intriguing aspects of the metallicity problem, the potential connection to dark matter. While dark matter itself is not believed to interact with metals in a conventional sense, some theories suggest that interactions between dark matter and normal matter could influence the way metals are distributed. If dark matter halos around galaxies play a role in trapping or dispersing metals, it could provide an explanation for some of the anomalies we observe. Moving closer to home, metallicity has profound implications for planetary systems and the emergence of life. Stars with higher metallicity are more likely to host rocky planets, as heavy elements are necessary for the formation of solid planetary cores. This raises an important question: could there be a metallicity threshold for habitability? If planets require a certain minimum amount of metals to support complex chemistry, then life, as we know it, might only be possible in regions of the universe with sufficient metallicity. Conversely, high metallicity can also lead to increased stellar activity and radiation, which could be detrimental to life. This paradox raises the possibility that the conditions necessary for life are not just about having the right type of planet, but also about being in the right type of stellar environment. If true, then the metallicity problem is not just a question of astrophysics. It could be a key factor in the search for extraterrestrial life. The fact that our own sun has a moderate metallicity suggests that it may be part of a sweet spot, where planetary formation and biological evolution are both possible. As we continue to explore these questions, new discoveries challenge our assumptions. Observations of distant galaxies using the James Webb Space Telescope, JWST, have already begun to reveal unexpected metallicity patterns in the early universe, suggesting that metal enrichment may have occurred much faster than previously thought. This could mean that our models of early star formation need to be revised, or that unknown processes accelerated the spread of metals in the first few 100 million years after the Big Bang. The metallicity problem is a reminder that the universe is far more complex than we ever imagined. It forces us to reconsider the mechanisms that shape galaxies, the processes that govern star formation, and the very conditions that make life possible. Every new observation adds another piece to the puzzle, but it also raises new questions, pushing the boundaries of our understanding. Ultimately, solving the metallicity problem may require more than just better telescopes. It may demand a fundamental shift in our understanding of cosmic evolution. Whether it involves new physics, unseen interactions, or an entirely different way of looking at the universe, one thing is certain: the mystery of metallicity is far from over. The metallicity problem remains one of the most perplexing astrophysical challenges, reaching across multiple disciplines of science, from cosmology and stellar evolution to planetary science and even astrobiology. The deeper we investigate, the more we realize that metallicity is not just a footnote in cosmic history. It is a defining characteristic of how the universe evolved and continues to evolve. It dictates the birth and death of stars, the formation of planetary systems, and possibly even the conditions necessary for life. One of the most intriguing aspects of metallicity is its role in the evolution of the first galaxies. In the earliest epochs of the universe, shortly after the Big Bang, the first stars, often referred to as population 3 stars, formed in an environment completely devoid of metals. These stars, composed purely of hydrogen and helium, were likely much more massive than modern stars, some reaching hundreds of times the mass of the Sun. The reason for this lies in the physics of star formation. In a metal-poor environment, gas cannot cool efficiently, which leads to the formation of only the most massive stars. These primordial stars burn their fuel quickly, live short and violent lives, and exploded as hypernovae, dispersing the first heavy elements into space. This process set off a chain reaction, leading to the birth of population 2 stars, stars with slightly higher metallicity, but still much lower than those we see today. Over time, continued cycles of star formation and supernovae enrich the universe further, leading to the population 1 stars that dominate galaxies like our own Milky Way. However, observations of ancient, metal-poor stars in the halo of our galaxy suggest that this process did not happen uniformly. Some of these stars have unexpectedly high abundances of certain heavy elements, such as europium, which is primarily produced in neutron-star mergers rather than supernovae. This suggests that some regions of the early universe may have been enriched in a very different way than previously thought. It raises the possibility that exotic astrophysical events, like collisions between neutron stars or even interactions with primordial black holes, played a role in shaping the chemical composition of galaxies. The distribution of metals in galaxies is another piece of the puzzle. Observations show that metallicity is not uniform, even within individual galaxies. In spiral galaxies like the Milky Way, metallicity tends to be highest in the central regions and gradually decreases toward the outer edges. This makes sense in the context of star formation, since the galactic center has undergone more cycles of stellar birth and death. It should be more metal-rich. However, there are anomalies. Some regions of galaxies, even far from the center, show unexpectedly high metallicity, while others remain surprisingly metal-poor despite their proximity to dense star-forming regions. One explanation for this involves galactic fountains, massive outflows of gas driven by supernova explosions that can carry metals high above the galactic disk, where they later cool and rain back down in different locations. This could explain why some regions of galaxies have seemingly random metallicity variations. However, this theory is difficult to confirm observationally, as it requires detailed measurements of gas motion on enormous scales. Another possibility is that past galaxy mergers have disrupted the normal distribution of metals. When galaxies collide, their gas clouds mix chaotically, triggering bursts of star formation while also redistributing elements in unpredictable ways. This could explain why some galaxies appear to have experienced unusual patterns of metal enrichment that do not align with standard models of stellar evolution. But perhaps the greatest mystery of all is why some stars defy all expectations when it comes to their metallicity. While the general trend is that older stars have lower metallicity and younger stars have higher metallicity, there are exceptions. Some ancient stars in the Milky Way halo have metallicities comparable to much younger stars, while certain young stars in the galactic disk appear far more metal-poor than they should be. These stars do not fit into any standard model of chemical evolution, leading to speculation that they may have originated in entirely different environments. One radical idea is that these stars were not born in the Milky Way at all, but were instead captured from smaller, merging dwarf galaxies. This would mean that the history of our own galaxy is far more complex than a simple model of continuous star formation and gradual enrichment. It suggests that the Milky Way has been shaped by a long history of galactic cannibalism, absorbing smaller galaxies and incorporating their stars into its structure. Another possibility is that these stars formed from gas clouds that were unusually metal-poor for reasons we do not yet understand. Some astronomers speculate that this could be due to variations in the mixing efficiency of heavy elements in the interstellar medium. If metals are not evenly distributed in gas clouds before they collapse to form stars, then it is possible for some stars to end up with much lower metallicity than others, even if they formed at the same time. Recent discoveries have also challenged our understanding of how metallicity affects planetary formation. For years, astronomers believed that metal-rich stars were far more likely to host planets, especially rocky planets like Earth. This idea was based on observations showing that exoplanetary systems tend to be found around stars with higher metallicity. However, more recent studies have found giant planets orbiting surprisingly metal-poor stars, suggesting that planetary formation can occur under a wider range of conditions than previously thought. This raises new questions about the role of metallicity in shaping habitable worlds. If metal-poor stars can still form planets, then perhaps the conditions necessary for life are more widespread than we assumed. On the other hand, the lack of heavy elements could mean that such planets have very different compositions, potentially affecting their atmospheres, magnetic fields, and even their ability to sustain liquid water. The metallicity problem also extends beyond individual stars and galaxies to the large-scale structure of the universe itself. Observations of the intergalactic medium reveal that vast amounts of metals exist between galaxies, yet the processes that distributed these elements across cosmic distances remain unclear. Some theories suggest that cosmic winds, powered by supermassive black holes, played a major role in spreading metals into deep space. Others propose that early cosmic structures, such as massive primordial gas clouds, facilitated the transport of metals long before galaxies fully formed. What is certain is that metallicity is not just a minor detail of astrophysics. It is a key to understanding the very nature of the universe. It influences everything from the formation of the first stars to the evolution of galaxies, the conditions necessary for life, and even the fate of the cosmos itself. If metallicity plays a role in the distribution of dark matter or the interactions between cosmic structures, it could be a crucial factor in determining how the universe will continue to evolve. As telescopes become more powerful and our ability to study distant galaxies improves, new discoveries will continue to reshape our understanding of this mystery. The James Webb Space Telescope is already providing unprecedented insights into the chemical composition of the earliest galaxies, revealing that metal enrichment may have occurred much faster than previously thought. Future missions, such as the planned Extremely Large Telescope, ELT, will allow us to measure metallicity in individual stars within distant galaxies, providing new data that could challenge or confirm our current theories. The metallicity problem is a reminder that even something as seemingly simple as the abundance of elements in a star can open up profound questions about the nature of the universe. It forces us to reconsider long-held assumptions, develop new theories, and explore possibilities that may have once seemed improbable. Whether it leads to the discovery of new physics, a better understanding of galaxy formation, or even clues about the existence of extraterrestrial life, one thing is certain: the mystery of metallicity is far from being solved. The implications of the metallicity problem extend into every corner of astrophysics, touching on topics as vast as galaxy evolution, the cosmic web, and even the fundamental forces that shape the universe. One of the most compelling aspects of this mystery is that it challenges our ability to construct a coherent narrative of cosmic history. The standard model of element formation, the idea that metals build up over generations of stars, is largely correct, but the strange exceptions and unexpected variations force us to confront gaps in our understanding. One of the most significant puzzles surrounding metallicity is the presence of extremely metal-poor stars in regions where we would expect much higher levels of metal enrichment. These stars, sometimes called stellar fossils, provide a unique window into the early universe, as they likely formed from gas that had been only lightly enriched by the first supernovae. But their very existence in metal-rich environments raises serious questions. How did these stars avoid the metal enrichment that should have occurred over billions of years? Why are some of them found in regions of the Milky Way that should have undergone multiple cycles of star formation and supernova-driven enrichment? One possible explanation is that these stars migrated over vast distances, either through galactic interactions or through long-term gravitational processes. Some astronomers propose that these stars originated in dwarf galaxies with unusually low star formation rates, where metal enrichment occurred very slowly. As the Milky Way absorbed these smaller galaxies, their low metallicity stars were deposited into the galactic halo, creating a patchwork of stellar populations with widely different metallicities. However, other theories suggest that some of these metal-poor stars could be even more ancient than previously thought, potentially dating back to the very first generation of stars. If this is true, it raises an even deeper mystery. Why did some pockets of the early universe remain metal-poor for so long? The answer might lie in variations in the initial conditions of the universe itself, differences in density, temperature, or even the distribution of dark matter that could have affected the rate at which the first stars formed and enriched their surroundings. Another mystery tied to metallicity is the apparent presence of anomalously metal-rich stars in regions where we would expect lower levels of heavy elements. These stars defy conventional models by showing unexpectedly high concentrations of specific metals, such as barium and strontium, which are typically produced in neutron star mergers or certain types of supernovae. The distribution of these elements suggests that some regions of the Milky Way, and possibly other galaxies, have undergone enrichment through exotic processes that we do not yet fully understand. One particularly intriguing possibility is that these unusual stars are the remnants of a now vanished population of high-mass stars that followed a completely different evolutionary path than what we see today. If so, it would suggest that the early universe had a much greater diversity of stellar types than previously believed. Some researchers have even speculated that interactions between stars and primordial black holes could have played a role in shaping the metallicity of certain stellar populations, though this remains highly theoretical. The role of metallicity in star formation itself is another major unsolved question. While we know that higher metallicity generally leads to smaller, cooler stars that burn their fuel more slowly, there are exceptions that challenge this rule. Some extremely metal-poor stars appear to be much larger and hotter than expected, while certain metal-rich stars show unusual temperature profiles that do not align with standard stellar models. This suggests that metallicity may interact with other physical processes in ways we do not yet fully understand. One hypothesis is that magnetic fields play a more significant role in star formation than we previously thought. If strong magnetic fields were present in certain regions of the early universe, they could have influenced how gas clouds collapsed, leading to variations in the metallicity of newly formed stars. Some evidence for this comes from observations of high-mass stars with extremely strong magnetic fields, which show unusual chemical compositions that may be linked to their formation environment. The connection between metallicity and planetary formation is another area of active research. For many years, astronomers believed that metal-rich stars were more likely to host planets, particularly terrestrial planets like Earth. This was based on the idea that elements like silicon, iron, and oxygen are essential for forming rocky worlds. However, recent discoveries have complicated this picture. Some metal-poor stars have been found to host giant planets, suggesting that planetary formation can occur even in environments with relatively few heavy elements. This raises profound questions about the conditions necessary for habitability. If planets can form around metal-poor stars, does this mean that potentially habitable worlds exist in a much wider range of environments than we previously thought? Or do these planets have fundamentally different compositions that might make life less likely? Some researchers suggest that metal-poor planetary systems might lack the necessary ingredients for strong magnetic fields or plate tectonics, which could impact their ability to sustain life over long periods. Metallicity also plays a crucial role in the life cycles of galaxies themselves. Observations of distant galaxies show that metallicity evolves over cosmic time, with younger galaxies generally having lower metal content than older ones. However, there are outliers, galaxies with unexpectedly high or low metallicities compared to what we would predict based on their age and star formation history. Some of these anomalies may be the result of mergers, while others could be influenced by powerful galactic winds that have either expelled metals into intergalactic space or brought in fresh, metal-poor gas from the cosmic web. One of the biggest questions in this field is how metals are distributed on the largest scales in the universe. Observations of the intergalactic medium, vast regions of space between galaxies, have revealed surprisingly high concentrations of metals, despite the fact that these regions should have very little star formation. This suggests that some process, possibly involving supermassive black holes or large-scale cosmic flows, has transported metals across immense distances. Understanding how this process works could provide new insights into galaxy formation, dark matter interactions, and even the ultimate fate of the universe. Another unsolved mystery is whether metallicity plays a role in the evolution of dark matter structures. Some theories suggest that interactions between dark matter and ordinary matter could have influenced the chemical enrichment of galaxies, potentially leading to variations in metallicity on a cosmic scale. If true, this could mean that studying metallicity might provide indirect clues about the nature of dark matter itself. In the coming years, new telescopes and observational techniques will allow us to probe these questions in greater detail than ever before. The James Webb Space Telescope has already begun providing unprecedented data on the chemical composition of the earliest galaxies, and future missions like the Extremely Large Telescope, ELT, will allow us to study metallicity in individual stars within distant galaxies. These advancements could revolutionize our understanding of how metals shape the universe, revealing new insights into everything from the first moments after the Big Bang to the processes that drive galaxy evolution today. Ultimately, the metallicity problem serves as a reminder that even something as seemingly simple as the abundance of elements in a star can open up profound questions about the nature of the universe. It forces us to rethink long-held assumptions, explore new theoretical models, and push the boundaries of our observational capabilities. Whether it leads to the discovery of new physics, a deeper understanding of cosmic history, or even hints about the conditions necessary for life, one thing is clear: the mystery of metallicity is far from being solved. The mystery deepens when considering the role of metallicity in the formation and evolution of the universe's most enigmatic objects: black holes, neutron stars, and exotic stellar remnants. Since heavy elements influence the cooling rate of gas clouds and determine the mass distribution of forming stars, they may also dictate the likelihood of extreme stellar phenomena. Metal-poor environments are believed to have produced more massive stars in the early universe, leading to a higher frequency of black hole formation. Yet, some black holes, including those in the Milky Way, are found in regions with unexpectedly high or low metallicities, suggesting that their formation history may involve unknown processes. One of the biggest implications of metallicity in this context is its role in supernova explosions. The final fate of a massive star, whether it becomes a neutron star, a black hole, or something even stranger, depends heavily on its metallicity. High metallicity stars experience stronger stellar winds, which strip away mass and prevent them from collapsing directly into black holes. Conversely, metal-poor stars retain more mass until the very end, increasing the likelihood of forming black holes. This could explain why some of the most massive black holes detected in the early universe appear to have formed much faster than expected, possibly from low metallicity progenitors that collapse directly instead of shedding mass through explosions. Even more puzzling is the existence of certain neutron stars with chemical signatures that do not align with conventional stellar evolution models. Some neutron stars exhibit unusually high concentrations of heavy elements like gold and platinum, which are typically produced in neutron star mergers. Yet, these stars appear in environments where such mergers should be rare, leading to speculation about unknown nucleosynthesis processes that might be at play. Could there be alternative pathways for the production of heavy elements that we have yet to discover? Another mystery concerns the role of metallicity in the enigmatic population of stars known as hypervelocity stars. These stars, which are traveling at speeds high enough to escape the Milky Way, are thought to originate from interactions with the supermassive black hole at the galaxy's center or from the tidal disruption of binary systems. However, some hypervelocity stars have metallicities that do not match their supposed birthplaces, suggesting that they may have been ejected from environments vastly different from what we would expect. This raises the possibility of unknown acceleration mechanisms or long-distance migrations that have yet to be fully understood. Looking beyond individual stars, the metallicity problem has profound implications for the large-scale structure of the cosmos. Observations of distant galaxies show that metallicity follows an intricate pattern across cosmic history, with some galaxies evolving faster than others. The discovery of ancient, metal-rich galaxies that seemingly defy expectations has led some astronomers to question whether our models of galactic evolution are incomplete. Some theories suggest that early galactic collisions, interactions with dark matter structures, or even exotic astrophysical phenomena could have enriched certain galaxies more rapidly than expected. The existence of anomalously metal-rich gas clouds in intergalactic space adds another layer to this mystery. These clouds, detected through quasar absorption lines, contain unexpectedly high concentrations of elements like carbon, oxygen, and iron, even in regions where star formation should have been minimal. Some scientists propose that galactic superwinds or cosmic magnetic fields may have transported metals over immense distances, but the exact mechanisms remain elusive. If metals can be spread so efficiently across the universe, what does this mean for our understanding of cosmic chemical evolution? On an even larger scale, the study of metallicity could provide crucial insights into the interplay between dark matter and ordinary matter. Some researchers speculate that variations in metallicity across different regions of space might be influenced by the distribution of dark matter, which affects the gravitational dynamics of galaxies and their ability to retain or expel metals. If true, metallicity could serve as an indirect probe for understanding the nature of dark matter itself, one of the greatest unsolved mysteries in physics. Future observations will be key to unraveling these mysteries. The James Webb Space Telescope is already shedding light on the metallicity of the first galaxies, revealing details about their chemical composition that were previously inaccessible. Meanwhile, next-generation observatories like the Extremely Large Telescope and the 30-meter telescope will allow astronomers to measure metallicity with unprecedented precision in distant cosmic structures. These advancements could help answer fundamental questions. How did metals first spread throughout the universe? What role did exotic astrophysical events play in shaping the chemical diversity we see today? And could metallicity ultimately provide a new window into the physics of dark matter, black holes, and the very structure of reality itself? As we continue to explore the mysteries of metallicity, it becomes clear that this puzzle is far more than a simple anomaly. It is a key to unlocking some of the deepest secrets of the cosmos. Whether it leads to the discovery of new physics, a revised understanding of stellar evolution, or a deeper connection between ordinary matter and the dark components of the universe, one thing is certain: the strange, unpredictable nature of metallicity will continue to challenge and inspire astronomers for generations to come. The deeper we look into the metallicity problem, the more we realize that it connects to nearly every major question in astrophysics. The peculiar chemical compositions of stars, the unexpected metallicity patterns in galaxies, and the role of heavy elements in shaping cosmic evolution all point to gaps in our understanding of how the universe works. Some of these gaps may be filled with new discoveries in nuclear physics, stellar evolution, or interstellar dynamics. But others may hint at even more profound truths, perhaps even new forces or fundamental principles that have yet to be uncovered. One of the most perplexing aspects of the metallicity problem is how it relates to the formation of planets. We know that metal-rich stars tend to have a higher probability of hosting planets, particularly gas giants like Jupiter and Saturn. This is because metals contribute to the formation of solid cores and protoplanetary disks, which are necessary for planet formation. However, there are notable exceptions to this trend. Some stars with extremely low metallicity have been found to host planets, challenging our models of planetary formation. How can planets form in environments that should, by all accounts, lack the necessary building blocks? This raises the possibility that unknown processes may allow certain elements to concentrate in specific regions, enabling planet formation even in unexpected conditions. Adding to the mystery, some exoplanetary systems have metallicities that do not match those of their host stars. This suggests that planetary material may have originated from a different region of space, perhaps through interstellar material exchange or migration events. If true, this would imply that planetary systems are not as isolated as once thought, and that material can be transported over vast cosmic distances. Could this mean that some planets, and even entire solar systems, are fundamentally different in composition from the stars they orbit? If so, what does this tell us about the origins of planets like Earth? The role of metallicity in habitability is another area of intense debate. Some researchers argue that a high metallicity environment is essential for the development of complex life, as it allows for the formation of key elements such as carbon, oxygen, and nitrogen. However, others propose that metal-poor environments could foster alternative biochemistries, leading to life forms unlike anything we know. If extraterrestrial life exists, could its chemistry be vastly different depending on the metallicity of its home star? Could there be worlds where silicon-based or even ammonia-based life has emerged due to unique metallicity conditions? Observations of ancient stars in the Milky Way have provided more surprises. Some of the oldest stars in our galaxy, known as Population 2 stars, have unexpectedly high levels of certain heavy elements. This is puzzling because these stars should have formed in an era when the universe was still largely devoid of metals. The presence of heavy elements suggests that early supernovae may have enriched their environments, far more efficiently than we previously thought. Alternatively, it could mean that these stars formed from gas that had been enriched by an unknown process, perhaps interactions with primordial black holes, dark matter, or exotic astrophysical phenomena that we have yet to identify. The discovery of population 3 stars, the first generation of stars in the universe, could provide crucial insights into the metallicity problem. These stars are believed to have been composed almost entirely of hydrogen and helium, with no heavy elements. However, despite decades of searching, no confirmed population 3 stars have ever been observed. Some scientists speculate that these stars may have been incredibly short-lived, rapidly collapsing into black holes before we could detect them. Others propose that they may still exist in hidden regions of the universe, obscured by cosmic dust or located in remote galaxies beyond our observational reach. If we can find and study these elusive stars, we may finally be able to understand how the first metals were created and how they spread across the cosmos. On an even larger scale, the metallicity problem challenges our understanding of galaxy formation and evolution. Some galaxies contain stars with wildly different metallicities, suggesting complex histories of mergers, interactions, and unknown astrophysical processes. The presence of metal-rich stars in metal-poor galaxies and vice versa raises questions about how galaxies exchange material, and whether unknown forces could be at play in redistributing elements across vast cosmic distances. Could metallicity anomalies hint at interactions with dark matter halos or even suggest the existence of previously unknown galactic structures? Moreover, metallicity may hold the key to solving one of the greatest mysteries of cosmology, the nature of dark matter. Some researchers propose that variations in metallicity across different regions of the universe could be influenced by the presence of dark matter, which may affect how galaxies retain or lose metals. If true, studying metallicity patterns could provide an indirect method for mapping dark matter distributions, bringing us closer to understanding its true nature. Could metallicity be the missing link between the visible and invisible components of the universe? Future missions will be essential in uncovering more about the metallicity problem. The next generation of telescopes, such as the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will allow astronomers to probe the metallicity of distant galaxies and stars with unprecedented precision. Meanwhile, advanced simulations using artificial intelligence and machine learning may help us model metallicity evolution across cosmic time, potentially revealing hidden patterns and relationships that were previously undetectable. As we push the boundaries of our understanding, one thing remains certain: the metallicity problem is not just an isolated astrophysical curiosity. It is a fundamental puzzle that ties into nearly every major question in cosmology, from the formation of the first stars to the nature of dark matter and the possibility of extraterrestrial life. The strange, unpredictable behavior of metals in the universe continues to defy our expectations, challenging us to rethink our assumptions about how the cosmos operates. Perhaps the solution to the metallicity problem lies in physics we have yet to discover. Could unknown nuclear reactions, exotic particle interactions, or even modifications to our understanding of gravity play a role? Could there be hidden cosmic mechanisms that redistribute elements in ways we cannot yet detect? Or could the metallicity problem be pointing us towards something even deeper, a fundamental principle of nature that has eluded us until now? One thing is clear: the more we study metallicity, the more questions we uncover. And as our technology advances, we may soon find answers that reshape our understanding of the universe itself. But until then, the mystery remains, hidden in the strange, unpredictable chemistry of the stars. The metallicity problem challenges our understanding of cosmic evolution in ways that go beyond traditional astrophysics. It touches on the origins of matter, the behavior of elements in extreme environments, and even the fundamental processes that shape the universe. If metals are not distributed as expected, what does this mean for our models of nucleosynthesis? Could there be unknown mechanisms driving the creation and dispersal of heavy elements? These questions take us to the very heart of stellar physics, supernova dynamics, and even the properties of space itself. One of the most perplexing aspects of this mystery is the role of supernovae in metal distribution. We know that Type II supernovae, the explosive deaths of massive stars, are responsible for producing many of the heavier elements we observe. However, the exact efficiency of this process is still debated. Some supernovae appear to enrich their surroundings far more than expected, while others seem to trap metals within their remnants. This could explain some of the strange metallicity variations seen in stars, but it raises another question: what determines whether metals are retained or expelled? Is it a matter of explosion energy, surrounding gas density, or some unknown variable? Additionally, neutron star mergers have been identified as a major source of certain heavy elements, such as gold and platinum. These events, which involve the collision of two dense stellar remnants, create conditions extreme enough to forge elements via the rapid neutron capture process, our process. However, observations suggest that neutron star mergers alone cannot account for all the heavy elements in the universe. This means there may be other, undiscovered sources of metal production. Could exotic astrophysical events, such as magnetar flares or primordial black hole interactions, contribute to metallicity in ways we have not yet considered? Another aspect of the metallicity problem lies in the Milky Way itself. Our galaxy exhibits complex metallicity patterns that defy easy explanation. Some regions are rich in heavy elements, while others are unexpectedly metal-poor. Even more puzzling is the discovery of hypermetal-poor stars in the Milky Way's halo, stars that seem to contain virtually no elements beyond hydrogen and helium. These stars likely formed from primordial gas clouds that were never significantly enriched, yet their existence within our galaxy raises a fundamental question: how did they survive in an environment where metals should be far more abundant? Did they form in isolated pockets of space untouched by supernovae? Or were they somehow transported into the Milky Way from another galaxy, bringing with them clues about early cosmic evolution? The metallicity problem also extends to intergalactic space. The interstellar medium, the vast regions of gas and dust between stars, contains traces of metals, but its metallicity varies in unexpected ways. Some intergalactic clouds appear to be metal-rich, despite being located in regions where no known star formation has occurred. This suggests that metals are somehow being transported across vast distances. Could galactic winds, black hole jets, or even cosmic filaments be responsible for moving heavy elements from one part of the universe to another? If so, how does this process work on a large scale, and what does it tell us about the interconnected nature of galaxies? Adding another layer of intrigue, some of the oldest galaxies in the universe display metal compositions that do not align with our current models. Observations of ancient galaxies using telescopes like the James Webb Space Telescope, JWST, have revealed unexpected metallicity levels, suggesting that metal enrichment occurred much earlier than previously thought. This challenges the idea that the first few billion years of cosmic history were dominated by metal-poor environments. Instead, it raises the possibility that unknown processes, perhaps early supermassive black hole activity or exotic stellar populations, may have accelerated metal production. If this is true, it would force us to rethink the timeline of element formation and the role of early galaxies in shaping the chemical evolution of the universe. One of the most radical possibilities is that metallicity variations could hint at new physics. If the distribution of metals does not match predictions, could this mean that unknown forces are at play? Some researchers speculate that interactions with dark matter could influence how metals are distributed. If dark matter interacts with ordinary matter in ways beyond simple gravitational effects, it could alter the way elements are retained or expelled from galaxies. Could dark matter halos be affecting the ability of galaxies to hold onto metals, creating the strange patterns we observe? Other theories suggest that the physics of nucleosynthesis itself may need revision. Could there be undiscovered nuclear reactions occurring in stars that alter the expected metallicity ratios? Are there unknown particle interactions affecting the way elements are formed? These possibilities may sound speculative, but history has shown that cosmic anomalies often lead to groundbreaking discoveries. After all, it was the unexplained behavior of galaxies that first led to the discovery of dark matter. Could the metallicity problem be pointing us toward another fundamental breakthrough? The implications of solving the metallicity problem extend far beyond astrophysics. If we can understand how metals form, distribute, and influence cosmic structures, we can refine our search for habitable worlds. metallicity plays a crucial role in determining whether planets can form, whether they can support atmospheres, and even whether they might harbor life. If metallicity is influenced by unknown processes, it could mean that planets form under a wider range of conditions than we currently assume. This could expand our definition of habitability and open new possibilities in the search for extraterrestrial life. At the same time, solving this mystery could provide insights into the ultimate fate of the universe. The distribution of metals affects star formation rates, galaxy evolution, and even the eventual depletion of stellar fuel. If metals are not behaving as expected, it could mean that our predictions about the distant future of the cosmos need adjustment. Will the universe continue forming stars for trillions of years? Or will metallicity-related processes hasten the decline of star formation? Future observations will be critical in unraveling these mysteries. Telescopes like the JWST, along with upcoming missions such as the European Space Agency's Plato and NASA's Roman Space Telescope, will provide deeper insights into the chemical composition of stars and galaxies. Meanwhile, laboratory experiments on Earth may help refine our understanding of nuclear reactions and element formation. By combining observational, theoretical, and experimental approaches, we may finally be able to solve the metallicity problem. Until then, this enigma remains one of the most tantalizing unsolved puzzles in astrophysics. Why do some stars contain metals they shouldn't? How do metals travel across cosmic distances? Could metallicity anomalies reveal hidden cosmic mechanisms? These questions push the boundaries of what we know, reminding us that the universe is still full of surprises waiting to be uncovered. The metallicity problem is not just a quirk of astrophysics, it is a fundamental challenge to our understanding of the cosmos. And as we continue to explore, we may find that its solution leads to discoveries even more profound than we ever imagined. The metallicity problem is a doorway to deeper questions about the universe, challenging our assumptions about cosmic evolution and hinting at unknown forces that shape the stars and galaxies we see today. It is not just an isolated quirk in astrophysics, but a fundamental inconsistency that suggests we may still be missing key pieces of the puzzle. Every strange metallicity pattern, every anomalous star with an unexpected composition, and every galaxy that defies our predictions is a clue, one that could lead us to a major breakthrough in our understanding of the cosmos. One of the most pressing questions in this field is the exact role of early stars, often referred to as population 3 stars, in shaping the metallicity of the universe. These stars, believed to be the first to form after the Big Bang, were composed almost entirely of hydrogen and helium, with virtually no heavier elements. Their existence has long been theorized, but direct observational evidence remains elusive. If these ancient stars truly existed, they would have played a crucial role in the first wave of metal production, seeding the universe with the elements necessary for later generations of stars and planets. However, if population 3 stars were more massive or more short-lived than expected, they might have enriched the universe much faster than our models predict. This could explain why some regions of space appear to have developed high metallicity levels surprisingly early in cosmic history. On the other hand, if these stars were fewer in number or behaved differently than we assume, it might help account for the existence of hypermetal-poor stars that seemingly formed in environments devoid of heavy elements. The problem is further complicated by the way metals cycle through galaxies. Once a supernova explodes, it scatters metals into space, enriching the surrounding gas clouds that will later form new stars. However, some observations suggest that metal distribution is far less uniform than our models predict. Certain regions of galaxies remain metal-poor despite being surrounded by metal-rich areas, implying that either some unknown process is preventing metal mixing or that metals are being transported away by mechanisms we do not fully understand. Galactic winds, driven by intense star formation and black hole activity, are one possible explanation. These powerful streams of gas can carry metals out of galaxies, depositing them into intergalactic space. But the details of this process remain unclear. How far do these metals travel? Are they eventually pulled back into galaxies, or do they drift indefinitely in the vast emptiness of space? If metals are being removed from galaxies at a higher rate than expected, this could help explain why some stars show lower metallicity levels than they should. At the same time, the role of cosmic inflows must be considered. Galaxies are not closed systems. They constantly interact with their surroundings, pulling in gas from intergalactic space. If this incoming gas is largely metalpoor, it could dilute the metallicity of newly forming stars, leading to unexpected variations. But where is this metalpoor gas coming from? Is it leftover material from the early universe, or is it being cycled through a process we have yet to identify? Another key factor in the metallicity problem is the behavior of black holes. Supermassive black holes, found at the centers of most large galaxies, have a profound influence on their surroundings. When they actively feed on matter, they release enormous amounts of energy, sometimes triggering powerful outflows of gas. These outflows could be responsible for ejecting metals from galaxies or preventing them from settling into new star-forming regions. If black holes are playing a larger role in metal distribution than we realize, this could mean that our models of galaxy evolution need significant revision. Furthermore, the strange metallicity patterns observed in certain star clusters suggest that something unusual may be happening at smaller scales. Some globular clusters, dense collections of ancient stars, exhibit unexpected metallicity variations, with some stars containing dramatically different levels of heavy elements than others. This contradicts the idea that all stars in a cluster should have formed from the same well-mixed gas cloud. Could unknown stellar processes be altering the metallicity of individual stars after their formation? Or are these clusters composed of stars that originated in entirely different environments, later merging into a single group? One of the most radical possibilities is that metallicity anomalies could be linked to exotic physics. Some researchers have proposed that interactions between dark matter and ordinary matter might influence metallicity in ways we do not yet understand. If dark matter has even weak interactions with baryonic matter, it could subtly alter the way metals are distributed in galaxies, creating the unexpected patterns we observe. This idea remains speculative, but if confirmed, it could provide one of the first direct clues about the nature of dark matter, a discovery that would revolutionize physics. The metallicity problem also has profound implications for the search for habitable planets. The composition of a star determines the types of planets that can form around it. Metal-rich stars are more likely to host rocky planets like Earth, while metal-poor stars may primarily produce gas giants or barren worlds. If metallicity is more variable than we expect, it could mean that the conditions for habitable planet formation are more diverse than previously believed. This would have major consequences for the search for extraterrestrial life, expanding the range of environments where life might exist. At the same time, metallicity is crucial for understanding the ultimate fate of the universe. The distribution of metals affects the rate of star formation, which in turn influences the long-term evolution of galaxies. If metals are being lost from galaxies at a higher rate than expected, it could mean that star formation will decline sooner than our models predict. On the other hand, if unknown mechanisms are replenishing metals, the universe may remain capable of forming new stars for far longer than we currently anticipate. Future research will be essential in solving these mysteries. Upcoming telescopes, such as the European Extremely Large Telescope, ELT, and the next generation of space observatories, will provide unprecedented insights into the chemical composition of stars and galaxies. Advanced computer simulations will help refine our models of metal production and distribution, while laboratory experiments on Earth may uncover new nuclear reactions that play a role in stellar evolution. Ultimately, the metallicity problem is more than just an astrophysical curiosity. It is a gateway to deeper questions about the fundamental workings of the cosmos. Whether it leads us to new discoveries about the first stars, the influence of black holes, or even the nature of dark matter itself, one thing is clear: the universe is far more complex and mysterious than we ever imagined. The metallicity problem remains one of the most perplexing mysteries in astrophysics, touching upon the very fabric of cosmic evolution. It challenges our understanding of how stars form, how galaxies evolve, and even how the building blocks of life itself are distributed throughout the universe. The implications extend far beyond mere chemical compositions. They influence planetary formation, the potential for extraterrestrial life, and the long-term fate of the cosmos. As we continue to probe deeper into this enigma, we are forced to reconsider some of our most fundamental assumptions about the nature of the universe itself. One of the most striking aspects of the metallicity problem is how it defies simple explanations. Traditional models suggest that metals should be relatively evenly distributed across the universe, given the processes of stellar evolution, supernova explosions, and galactic mixing. Yet, time and time again, astronomers have found unexpected anomalies. Some stars are bafflingly metal-poor despite residing in metal-rich environments, while others exhibit metal abundances that seem impossible given their estimated ages. These inconsistencies suggest that our current models are missing something crucial, perhaps an unknown process that influences metallicity in ways we do not yet understand. A key part of this puzzle is the role of cosmic inflows and outflows. In the vast cosmic web, galaxies are not isolated entities. They constantly exchange matter with their surroundings. The intergalactic medium, the tenuous gas that fills the space between galaxies, acts as a vast reservoir of raw material, fueling new star formation. If metal-poor gas is constantly being funneled into galaxies, it could explain why some regions remain surprisingly deficient in heavy elements despite billions of years of stellar activity. Conversely, galactic outflows, driven by powerful events such as supernovae and black hole activity, can expel metals into intergalactic space, removing them from the star-forming regions of galaxies. If these outflows are stronger or more efficient than we currently believe, they could be responsible for the unexpected metal-poor stars we observe. Some galaxies, particularly those experiencing rapid star formation, may be losing metals at a much higher rate than expected, leading to strange metallicity profiles. Adding to the complexity, not all metals produced in stars may be immediately available for future generations of stellar formation. Some heavy elements may become trapped in dense molecular clouds or locked away in long-lived objects such as planets and black holes. This could create hidden reservoirs of metals that are not accounted for in our current models, skewing our understanding of metallicity evolution. Moreover, the metallicity problem intersects with another major cosmic mystery: the nature of the first stars. Population 3 stars, if they existed as theorized, would have been the primary drivers of early metal enrichment in the universe. However, despite extensive searches, no definitive population 3 stars have ever been observed. If they were more massive or short-lived than expected, they might have rapidly dispersed their metals, leaving little direct evidence behind. On the other hand, if they were less common than our models predict, it could explain why some stars today still exhibit extremely low metallicity. The problem also extends beyond individual stars to entire galaxies. Observations of distant galaxies, those seen as they existed billions of years ago, have revealed surprising metallicity levels. Some young galaxies appear to have already accumulated high metal content, suggesting that metal production occurred much faster than expected. Others remain puzzlingly metal-poor despite being well into their evolutionary lifespans. These inconsistencies suggest that metallicity evolution is not a simple, linear process but is instead influenced by a wide range of dynamic factors. One possible explanation is that different galaxies experience different rates of star formation and metal enrichment depending on their environments. Galaxies in dense clusters, for example, may undergo more frequent mergers and interactions, accelerating the mixing and redistribution of metals. Isolated galaxies, on the other hand, may experience slower metal enrichment, leading to lower than expected metallicity levels. The role of dark matter in shaping these processes is still poorly understood, but it may play a crucial role in regulating how metals are distributed across cosmic structures. Another intriguing possibility is that metallicity variations could be linked to exotic physics beyond our current understanding. Some researchers have speculated that interactions between ordinary matter and dark matter might influence metal enrichment in ways we do not yet comprehend. If dark matter has even a weak interaction with baryonic matter, it could subtly alter the processes of star formation and metal mixing, leading to the strange metallicity patterns we observe. The metallicity problem also has profound implications for the search for extraterrestrial life. The abundance of metals in a star system plays a crucial role in determining the types of planets that can form. Metal-rich stars are more likely to host rocky planets, which are considered the most likely candidates for life as we know it. If metallicity varies more widely than we currently believe, it could mean that habitable planets are more, or less, common than we think. In addition, metallicity influences the stability and longevity of planetary systems. High metallicity stars are more likely to form planets with strong magnetic fields, thick atmospheres, and active plate tectonics, all factors that may be crucial for sustaining life. On the other hand, extremely metal-poor stars may be more prone to hosting gas giants or barren worlds, reducing the likelihood of habitable conditions. If we can solve the metallicity problem, it may provide key insights into where we should focus our search for alien life. Future observations will be essential in unraveling this mystery. Next-generation telescopes, such as the James Webb Space Telescope, the European Extremely Large Telescope, and upcoming space-based observatories, will provide unprecedented insights into stellar compositions across different cosmic epochs. By analyzing the spectra of distant galaxies and individual stars, astronomers hope to map out metallicity evolution in greater detail, identifying patterns that could point toward new physical processes at play. Advances in computational modeling will also play a crucial role. As our simulations of galaxy formation and evolution become more sophisticated, they may reveal unexpected factors influencing metallicity distribution. By testing different scenarios, such as varying supernova yields, alternative star formation rates, and exotic dark matter interactions, scientists can refine our understanding of how metals are produced, transported, and incorporated into new generations of stars. At its core, the metallicity problem is a testament to the ever-evolving nature of science. Every new discovery, every anomaly, and every unexpected observation forces us to refine our theories and seek deeper truths about the universe. It is a reminder that, despite our vast strides in understanding the cosmos, there is still so much we do not know. The fact that something as seemingly straightforward as the distribution of metals and stars remains an open question underscores just how complex and dynamic the universe truly is. Ultimately, solving the metallicity problem may require a fundamental shift in our understanding of astrophysics. Whether it leads us to new insights about the first stars, the role of black holes, the influence of dark matter, or even the conditions for life beyond Earth, one thing is certain: this mystery will continue to challenge and inspire astronomers for generations to come. The metallicity problem remains a cornerstone of astrophysical inquiry, interwoven with the grand tapestry of cosmic evolution, galactic formation, and the underlying mechanisms of stellar life cycles. The unexpected variations in metal abundance across different stellar populations defy our conventional models, prompting astronomers to rethink how metals are synthesized, dispersed, and retained within galaxies. This enigma is not just an isolated puzzle, it is a fundamental question that could reshape our understanding of the forces that have governed the universe since its earliest moments. One of the most profound implications of the metallicity problem is its connection to the cosmic timeline. When we look at stars and galaxies, we are essentially peering back in time, witnessing the chemical footprints left behind by billions of years of stellar evolution. If metals were distributed uniformly according to our standard models, then stars born within the same era and environment should exhibit relatively similar metallicity. Yet, what we observe is a striking deviation from this expectation. Some stars exhibit metal abundances far greater than their age and surroundings would predict, while others appear nearly devoid of heavy elements despite existing in metal-rich regions. This inconsistency suggests that metal enrichment is neither a simple nor a uniform process. One possible explanation lies in the chaotic nature of star formation. When a new generation of stars is born, they inherit the chemical compositions of the surrounding interstellar medium. However, the interstellar medium itself is constantly changing, influenced by the explosions of previous generations of stars, supernova-driven winds, and even the accretion of extragalactic material. If certain regions experience uneven metal mixing, then stars forming from these clouds may exhibit wildly different metallicities even if they originate in the same galactic neighborhood. Another major factor at play is the role of dwarf galaxies. These small, low-mass galaxies serve as cosmic building blocks, often merging with larger galaxies over time. Observations suggest that many of the most metal-poor stars in the Milky Way may have originated in these dwarf galaxies before being absorbed into the galactic halo. If these smaller galaxies experience delayed or inefficient metal enrichment, perhaps due to weaker star formation bursts or more effective metal loss via galactic winds, then their stars would naturally exhibit lower metallicity even when incorporated into a larger, more metal-rich system. Interestingly, some studies indicate that certain stars may have been polluted by their binary companions. In binary star systems, one star can transfer material to its partner, altering its apparent chemical composition. If a metal-rich companion undergoes a supernova explosion or sheds its outer layers through stellar winds, its metals can be absorbed by the surviving star, leading to unexpectedly high metallicity readings. This mechanism could explain some of the strange outliers observed in metal-poor regions, stars that, according to their age and location, should not be as metal-rich as they appear. Beyond these internal processes, extragalactic interactions may also play a role in shaping metallicity. When galaxies collide and merge, their gas and stellar populations become intertwined, leading to complex chemical mixing. Some studies suggest that major mergers can trigger bursts of star formation, leading to rapid metal enrichment in certain regions while simultaneously diluting metals in others. If the metallicity variations we observe today are influenced by ancient galactic collisions, then solving this puzzle may require a much deeper understanding of galaxy evolution over cosmic timescales. The metallicity problem also challenges our understanding of cosmic inflation and the distribution of matter in the early universe. If population 3 stars were responsible for the initial wave of metal enrichment, their impact should be visible in the metal-poor stars we observe today. However, the lack of direct evidence for population 3 stars, combined with the strange metallicity variations across different stellar populations, raises an intriguing possibility. Could there be alternative pathways for metal enrichment that we have yet to uncover? One speculative idea is that certain forms of exotic physics may be influencing metallicity distribution. Some theories propose that early universe processes, such as interactions between dark matter and normal matter, could have affected how metals were retained or dispersed in the first galaxies. If dark matter plays an active role in regulating gas cooling and star formation, it could indirectly influence the metallicity of emerging stars in ways we do not yet fully grasp. Moreover, the study of metallicity ties directly into the search for habitable worlds. The formation of planets, particularly rocky terrestrial planets like Earth, is heavily dependent on the availability of heavy elements. Stars with low metallicity are less likely to host Earth-like planets, as the raw materials necessary for planet formation are scarcer. This raises a crucial question: if metallicity is more variable than previously believed, does that mean habitable planets are rarer than we thought? Or does it imply that certain regions of the universe may be more conducive to life than others? The answer to this question could redefine the search for extraterrestrial life. If metal-rich stars are more likely to host planets with stable atmospheres and protective magnetic fields, then regions of the universe with naturally higher metallicity could be prime targets for astrobiological exploration. Conversely, if planets can form even in low metallicity environments through mechanisms we have yet to understand, then the potential for life could extend far beyond our current expectations. Upcoming missions will provide critical insights into this mystery. The James Webb Space Telescope, with its ability to peer into the atmospheres of exoplanets and analyze distant galaxies in unprecedented detail, may reveal new clues about how metals are distributed across cosmic structures. Meanwhile, next-generation spectroscopic surveys will allow astronomers to map metallicity across the Milky Way and beyond, identifying patterns that could point toward new physical processes at work. As we continue to probe deeper into the metallicity problem, we are reminded of just how much we have yet to learn about the cosmos. What began as a seemingly straightforward question about metal distribution has evolved into a profound mystery that touches upon the origins of stars, the evolution of galaxies, and even the conditions necessary for life itself. The more we investigate, the more we realize that metallicity is not just a byproduct of stellar evolution, it is a fundamental key to understanding the very nature of the universe. The metallicity problem challenges the very foundation of our understanding of cosmic evolution. It forces us to reconsider how metals, elements heavier than hydrogen and helium, are synthesized, distributed, and recycled within the universe. The strange and unexpected metal compositions found in certain stars push astrophysicists to explore alternative theories beyond standard stellar evolution models. As new observational data emerges, the complexity of the metallicity problem only deepens, suggesting that multiple factors, including galactic dynamics, interstellar medium interactions, and even exotic physics, may play a role in shaping the chemical diversity we observe. One major aspect of the metallicity puzzle lies in the structure of the Milky Way itself. The galaxy is not a homogeneous collection of stars but rather a vast and dynamic system with distinct components: the thin disk, the thick disk, the halo, and the bulge. Each of these regions exhibits different metallicity distributions, which can sometimes defy expectations. For instance, the thick disk contains older stars, yet many of them have higher metallicities than expected for their age. The galactic halo, composed largely of ancient stars, contains some of the most metal-poor stars known, but surprisingly, a fraction of them exhibit metallicities comparable to much younger stars in the disk. One possible explanation for these anomalies lies in the concept of radial migration. In this model, stars do not remain fixed in their birthplaces. Instead, they move across different galactic regions due to interactions with spiral arms, bar structures, and other gravitational influences. If metal-rich stars originally formed in the inner regions of the galaxy where metals are more abundant but later migrated outward, this could explain the presence of unexpectedly high metallicity stars in regions where they seemingly do not belong. Conversely, metal-poor stars from the outer regions could have moved inward, further complicating the overall metallicity gradient. Another critical factor influencing metallicity distribution is the process of galactic mergers. Throughout its history, the Milky Way has absorbed numerous smaller galaxies, many of which brought their own stellar populations with unique chemical signatures. Some of these smaller galaxies had limited star formation, leading to inefficient metal production, while others may have lost significant amounts of metals through galactic winds driven by supernova explosions. When these galaxies merged with the Milky Way, their stars became part of the larger galactic structure, but their metallicity patterns remained distinct. This merger history may explain why some stars in the galactic halo exhibit metallicities that do not match those of the surrounding stellar populations. Looking beyond our own galaxy, observations of metal-rich stars in distant galaxies present further complications. Studies of early galaxies suggest that metal enrichment happened faster than previously thought, with some galaxies reaching high metallicities within just a few 100 million years after the Big Bang. This contradicts traditional models that predict a more gradual metal accumulation over billions of years. If metals were produced and dispersed more rapidly than expected in the early universe, this could imply that supermassive stars, hypernovae, or even unknown astrophysical processes played a significant role in early chemical evolution. The nature of the first stars, known as population 3 stars, is also deeply connected to the metallicity problem. These primordial stars, composed entirely of hydrogen and helium, were responsible for producing the first batch of heavy elements. However, despite extensive searches, no direct evidence of surviving population 3 stars has been found. If these stars truly existed, their chemical signatures should be visible in the oldest stars still present today. Yet, the lack of observational confirmation suggests either that these stars were incredibly short-lived and massive or that their metal contributions were somehow diluted in ways we do not yet understand. One alternative explanation involves the role of cosmic inflows and outflows. Galaxies constantly interact with the intergalactic medium, drawing in pristine hydrogen gas while expelling enriched material through supernova-driven winds. If these inflows and outflows were asymmetric or varied in intensity over time, they could create local metallicity variations that defy traditional chemical evolution models. For example, if a galaxy rapidly accreted metal-poor gas from its surroundings, this could temporarily lower its overall metallicity, even if previous generations of stars had already produced significant amounts of metals. Additionally, the presence of exotic astrophysical events could offer new insights into the metallicity puzzle. Some theorists have suggested that unusual metal distributions may be linked to rare phenomena such as magnetorotational supernovae, which generate extremely high levels of certain heavy elements. Others propose that direct collapse black holes, massive black holes formed without a supernova explosion, may have played a role in selectively enriching some regions of the universe while leaving others relatively untouched. The implications of the metallicity problem extend beyond astrophysics and into the search for extraterrestrial life. If metallicity influences planet formation, then the distribution of habitable worlds across the universe may not be as uniform as once assumed. Metal-rich regions may be more likely to host Earth-like planets, while metal-poor environments could favor different types of planetary systems, perhaps dominated by gas giants or exotic worlds unlike anything seen in our solar system. Understanding how metallicity shapes planetary formation is crucial for refining the criteria used in the search for life beyond Earth. As observational technology continues to advance, future telescopes such as the European Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope will provide unprecedented insights into the metallicity problem. High-resolution spectroscopic studies will allow astronomers to analyze the chemical compositions of stars with greater precision, potentially uncovering hidden patterns that could reveal the underlying mechanisms behind metallicity variations. Ultimately, the metallicity problem serves as a reminder that the universe is far more complex than our models often suggest. Every unexpected observation challenges us to refine our theories, explore new possibilities, and deepen our understanding of cosmic history. Whether the solution lies in unseen astrophysical processes, unknown stellar phenomena, or even fundamental physics beyond our current grasp, the search for answers continues to push the boundaries of human knowledge. The metallicity problem remains one of the most persistent challenges in modern astrophysics, with implications that reach into nearly every aspect of our understanding of the cosmos. As astronomers continue to observe more metal-rich and metal-poor stars in unexpected locations, the underlying complexity of the issue only grows. The traditional models of stellar evolution, chemical enrichment, and galactic dynamics must be re-examined in light of these findings, and new theories must be tested against the ever-expanding observational data. One of the most pressing questions is why certain stars exhibit metallicities far different from what standard models would predict based on their age, location, and evolutionary history. One particularly perplexing aspect of the metallicity problem involves hypermetal-poor stars, which contain virtually no elements heavier than hydrogen and helium. These ancient stars, often found in the galactic halo, should theoretically have formed from the remnants of the first generation of stars, population 3 stars, yet their compositions suggest an even more complex history. Some of these stars contain trace amounts of elements such as carbon and oxygen but almost no iron, an anomaly that cannot be easily explained by standard supernova enrichment models. One possible solution is that these stars formed from gas clouds enriched by an unusual type of supernova, such as a faint supernova, which produces only light elements while leaving behind little to no iron. Conversely, there are stars that appear to be too metal-rich for their environment. These stars, sometimes referred to as anomalous metal-rich stars, are found in regions where the average metallicity is much lower. One possible explanation for their existence is stellar migration, where stars move away from their birthplaces due to gravitational interactions with the galactic disk, spiral arms, or even passing molecular clouds. However, some metal-rich stars appear in locations where migration alone cannot fully account for their presence. This suggests that isolated pockets of metal-rich gas may have existed in the early universe, allowing for localized bursts of high metallicity star formation. The role of supernovae in shaping metallicity distributions is also a subject of ongoing investigation. Different types of supernovae contribute different elements to the interstellar medium. Core collapse supernovae, which result from the deaths of massive stars, produce large amounts of oxygen, magnesium, and silicon, while Type Ia supernovae, caused by white dwarf explosions, contribute heavier elements such as iron and nickel. The timing and frequency of these supernovae in different galactic regions may create unexpected metallicity patterns, especially if certain types of supernovae were more common in the past than they are today. Another intriguing aspect of the metallicity problem is its connection to planet formation. The presence of metals plays a crucial role in the formation of rocky planets, as elements like iron, silicon, and carbon are essential building blocks for terrestrial worlds. Observations have shown that metal-rich stars are more likely to host exoplanets, particularly gas giants like Jupiter and Saturn. However, recent discoveries have challenged this trend, with some metal-poor stars hosting unexpected planetary systems. This raises the question of whether alternative planet formation mechanisms may exist in environments with low metal abundances. The search for extraterrestrial life is also deeply tied to the metallicity problem. If planets require a certain threshold of heavy elements to develop complex chemistry, then regions of the universe with low metallicity may be less likely to support life. On the other hand, if life can arise in metal-poor environments, then the range of potentially habitable worlds may be much broader than previously thought. Understanding how metallicity influences planetary habitability is essential for refining the targets of future space missions in the search for biosignatures beyond Earth. The study of metallicity extends beyond individual stars and galaxies. The intergalactic medium, the vast expanse of gas between galaxies, also contains traces of metals, which provide clues about the large-scale processes that distribute elements across the cosmos. Observations of distant quasars have revealed metal absorption lines in the spectra of intergalactic gas clouds, indicating that metals have been present in the universe since its earliest epochs. The mechanisms responsible for spreading these metals over vast distances remain a topic of debate, with possibilities including galactic winds, cosmic filaments, and even interactions between dark matter and ordinary matter. One of the most exciting frontiers in metallicity research is the use of next-generation telescopes to probe the earliest epochs of star formation. The James Webb Space Telescope, JWST, has already begun detecting galaxies from the first few 100 million years after the Big Bang, providing unprecedented insights into the chemical evolution of the universe. Future missions, such as the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will allow astronomers to analyze the metallicity of stars and galaxies with even greater precision, potentially uncovering new clues about the origins of heavy elements and the processes that shape the cosmos. In addition to observational advances, theoretical models are also evolving to address the metallicity problem. Computational simulations of galaxy formation and evolution are becoming increasingly sophisticated, incorporating complex feedback mechanisms from supernovae, black holes, and interstellar turbulence. These models aim to replicate the observed metallicity distributions in real galaxies, helping to identify the key processes responsible for the anomalies seen in metal-rich and metal-poor stars. Ultimately, the metallicity problem is not just a challenge for astrophysics. It is a gateway to deeper questions about the nature of the universe. Understanding how elements form, how they spread, and how they influence the development of stars, planets, and life itself is one of the fundamental goals of modern cosmology. Every new discovery, whether it be an ancient metal-poor star, a surprisingly metal-rich exoplanet, or a distant galaxy with unexpected chemical compositions, brings us closer to unraveling the mysteries of metallicity and the cosmic story it tells. The metallicity problem is not merely a curiosity of astrophysical observations. It is a profound challenge to our understanding of how the universe evolved from a primordial soup of hydrogen and helium into the complex cosmos we observe today. The very existence of stars with anomalous metallicity suggests that our models of galactic chemical evolution may be incomplete or require significant refinement. As we continue to probe deeper into the mysteries of stellar composition, we are forced to confront fundamental questions about the processes that govern the formation and distribution of heavy elements throughout the universe. One of the most perplexing aspects of the metallicity problem lies in the behavior of metal-poor stars. In theory, these stars should be relics of the earliest generations of stellar formation, objects that provide a direct link to the conditions of the early universe. Yet, some of the lowest metallicity stars we have observed possess compositions that do not fully align with expectations. The presence of carbon-enhanced metal-poor (CMP) stars, for example, challenges traditional enrichment models. These stars contain high levels of carbon but very little iron, which suggests that they may have formed from gas that was enriched by unusual or selective nucleosynthesis events, such as faint supernovae or asymptotic giant branch (AGB) stars. Adding to the complexity, certain metal-poor stars exhibit unexpected isotopic ratios of heavier elements, such as strontium and barium. These elements are typically associated with slow neutron capture processes, the S process, or rapid neutron capture processes, the R process, both of which occur in very different astrophysical environments. Some researchers propose that these anomalies could be linked to early neutron star mergers, which release large amounts of R process elements into the surrounding interstellar medium. If confirmed, this would suggest that such catastrophic events played a more significant role in early chemical enrichment than previously believed. On the opposite end of the spectrum, metal-rich stars defy expectations in different ways. While it is well established that younger stars tend to be more metal-rich due to the gradual buildup of heavy elements over cosmic time, certain stars exhibit metallicities that are surprisingly high for their age and location. Some of these stars are found in the thick disk of the Milky Way, a region that should primarily contain stars with intermediate metallicities. Their presence suggests that either rapid and localized bursts of metal-rich star formation occurred or that they were somehow transported from other regions of the galaxy. Stellar migration is one potential explanation for these anomalies. Over time, stars can shift from their birthplaces due to interactions with spiral arms, giant molecular clouds, and even the gravitational influence of the galactic bar. However, in some cases, the metallicity differences between migrating stars and their surrounding stellar populations are too stark to be easily explained by standard migration mechanisms. Some astronomers speculate that these stars may have originated from smaller satellite galaxies that were later accreted by the Milky Way. If true, this would mean that the history of our galaxy is even more chaotic and complex than previously assumed, with metal-rich and metal-poor stellar populations being mixed together through a series of mergers and interactions. Beyond the Milky Way, the metallicity problem extends to the broader cosmic environment. The interstellar and intergalactic mediums contain metal distributions that challenge our understanding of element dispersal. Some regions of space appear to be enriched beyond expectations, while others remain surprisingly metal-poor. The mechanisms responsible for distributing metals across vast cosmic distances remain a subject of debate, with possibilities including galactic winds driven by supernovae, large-scale cosmic filaments funneling enriched gas, and even the role of dark matter in shaping the flow of heavy elements. One particularly intriguing mystery is the existence of highly metal-poor galaxies in the modern universe. Given that heavy elements have been steadily accumulating over billions of years, such galaxies should be exceedingly rare. Yet, astronomers have identified several dwarf galaxies that contain surprisingly low metallicities, suggesting that they have somehow remained isolated from the broader processes of chemical enrichment. These galaxies may provide crucial insights into primordial star formation and the conditions of the early universe, acting as time capsules that preserve the chemical signatures of the first few billion years of cosmic history. On a more fundamental level, the metallicity problem also touches on questions related to dark matter and dark energy. The distribution of metals within and between galaxies is influenced by gravitational interactions that may be shaped by the presence of unseen mass. Some researchers propose that differences in metallicity distribution could offer indirect evidence for the behavior of dark matter on galactic and intergalactic scales. If certain anomalies in metal-rich and metal-poor regions cannot be explained by known astrophysical processes, it could suggest that dark matter plays a more active role in shaping the universe than previously thought. The implications of the metallicity problem extend even to the origins of life itself. The elements that make up biological molecules, carbon, nitrogen, oxygen, phosphorus, and others, are products of stellar nucleosynthesis. If certain regions of the universe have significantly lower metallicities, it raises questions about the potential for life to emerge in these environments. Could life form in a metal-poor system, where the necessary elements for biochemistry are scarce? Or is there a threshold of metallicity beyond which complex chemistry becomes impossible? These questions are central to the search for extraterrestrial life and the broader field of astrobiology. With the advent of next-generation telescopes and observational technologies, astronomers are poised to make significant strides in resolving the metallicity problem. The James Webb Space Telescope has already begun identifying early galaxies with unexpected metallicities, providing valuable data on the evolution of heavy elements across cosmic time. Future instruments, such as the extremely large telescope and the 30-meter telescope, will allow scientists to measure the metallicity of individual stars in unprecedented detail, offering new clues about the processes that govern element formation and distribution. Theoretical advancements are also playing a crucial role. Computational models of galaxy evolution now incorporate increasingly sophisticated simulations of stellar feedback, supernovae, and interstellar gas dynamics. By comparing these models to observational data, researchers can refine their understanding of how metals are produced, dispersed, and recycled within galaxies. Some theories suggest that certain overlooked processes, such as high-energy cosmic rays or magnetohydrodynamic effects, may significantly influence the movement of heavy elements in ways not previously considered. Despite all these efforts, the metallicity problem remains an open question, one that challenges the very foundations of modern astrophysics. It forces us to reconsider our assumptions about stellar evolution, galaxy formation, and the nature of the universe itself. Every new discovery, whether it be a hypermetal pulsar, a metal-rich rogue planet, or an unexpectedly enriched intergalactic cloud, adds another layer to this cosmic puzzle. The search for answers continues, driven by the fundamental human desire to understand where we came from and how the universe has evolved into the rich and complex structure we observe today. As new telescopes come online and new models are tested, one thing is certain: the metallicity problem will remain at the forefront of astrophysical research for years to come. It is a mystery that touches on the deepest aspects of cosmic evolution, from the formation of the first stars to the emergence of habitable worlds. Solving it will require a combination of cutting-edge observations, innovative theoretical work, and perhaps even a paradigm shift in our understanding of how the universe assembles its building blocks. Until then, the strange and unexpected metallicities of stars across the cosmos will continue to challenge our perceptions, hinting at secrets that have yet to be uncovered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.